Right, so welcome to this public lecture. My name is András Juhász. I was a student of Zoltán. And in 2004, there was a clay summer school here, which was a formative experience for many researchers in my generation that was organized by András Lipschitz. And there were two introductory lecture series into Heegaard Floer homology given by Zoltán and Peter. So Peter is giving a panorama talk about Heegaard Floer homology, and I'm really excited to hear how the landscape has changed in the past 22 years.
Well, thank you all. I'm supposed to give a panorama talk with PDF slides, and I'm supposed to not move from here. So these are three things I don't know how to do. So we'll see how they combine. But I would like to thank the organizers for inviting me to this wonderful low-dimensional topology conference. It's a special honor to be back in Budapest, this city where I spent so much time in my youth and where people speak a normal language and eat normal food. And it's really a special honor to be in this almost holy building. András took me yesterday to see some of the collections, and it's really breathtaking what the history of this place. So really, if there's anything I could possibly complain about, it would only be that this is not the occasion to celebrate András and Zoltán's 60th birthday, and it will not be an opportunity for me to celebrate more than 30 years of friendship and mathematical kinship with two of my best math buddies. But that would not be appropriate to celebrate that because this is not a birthday conference. So, if it were, I would talk about our origin story. So András, Zoltán, and I were graduate students in the early 90s. The three of us were in New Jersey, and we were interested in understanding Donaldson theory, which gauge theory of four manifolds, and it was a really exciting time. There were these tremendous breakthroughs done in low-dimensional topology, but there were very few people who were plugged into this relatively obscure theory. So the three of us were very lucky to work with John Morgan. He was very gracious to put up with these three intruders from New Jersey, and we worked with him. He was at Columbia, which was fortunately not a difficult train ride from New Jersey. So we got our PhDs in 1994, and we went our separate ways. Zoltán went to Princeton for an instructorship, and I went to Caltech to work with Tom Rufka, and András went to Irvine to work with Ron Stern. But Irvine and Caltech were not far in those days, so there were joint seminars, lots of joint activity, so we got to hang out. But soon after we graduated, maybe it was November 1994, there was this traumatic event which rocked mathematics. So again, we were told about prehistoric times. Probably most of you weren't even born then. But this was this it was like when the comet hit and the dinosaur extinction. The gauge theory community was rocked by the introduction of the Seiberg-Witten equation. And everything we were doing had to be done differently. So gone were the beautiful non-abelian gauge groups, gone were the Uhlenbeck compactifications. We had to learn what a spinor was, what a spin C structure was, and basically we had to reevaluate all of our tools that we had been using to study smooth four-manifold topology. And I don't think I can fully convey to you the trauma of that event. So here are some photos from the time. This is John Morgan and Zoltán reevaluating their mathematical tools on the beach of Gukova, and I hope I'm not violating the dress code of this hallowed place, to also share with you a picture of András and Sylvie also reevaluating the tools they were using. So anyway, so Heegaard Floer homology was our attempt with Zoltán. We started working together in the fall of 1997. I was at the Institute at the time, he was at Princeton, and we started developing Heegaard Floer homology to give a geometric framework for gauge theory. So we wanted to understand topologically what the physicists were telling us to do. What was the meaning, the geometric meaning behind it. So here's a picture from Princeton in 1998, and as a bit of prehistory, in fact, that's a photo taken at the house of Louise Morse, Marston Morse's widow. We were at a party there. So anyway, so that was the introductory portion of my talk. So any family members of Zoltán's are welcome to either leave or completely tune out. And I will now, again, so I was struggling with what panorama means. One thing it means is that I should put a lot of pictures in. But one thing is that maybe I should say what the definition of Heegaard Floer homology is for those 3 or 4 people who've never seen it before. So, so Heegaard Floer homology was a way of describing this 3-manifold invariant in terms of combinatorial data that describe a 3-manifold. So what's a combinatorial way of describing a 3-manifold? Well, the Heegaard diagrams are a combinatorial way of describing a 3-manifold. So you start with an oriented surface of genus G, and you take 2 G tuples of curves. So in this case, genus is 2, and I've just drawn the 2 alpha curves. They're supposed to be homologically linearly independent G curves embedded. You have alpha 1 to alpha G, and you've got beta 1 through beta G. And together, that data specifies a closed 3-manifold. So observe that the alpha circles are all sort of simple looking, and the beta circles are also all simple looking, but the beta circles might look very complicated from the perspective from which the alpha curves look simple. So, individually, the alphas and the betas are standard, but when you put the pictures together, they can be complicated. So here's an example. So this is a genus 2 surface. You're supposed to imagine that I can use my pointer. That's a handle that runs from here to here. There's a handle that runs from here to here. So this curve labeled, this interval labeled alpha 1 closes up to give you a circle through that handle. The interval labeled alpha 2 closes up to give you a circle called alpha 2. And there are also 2 beta circles, which from this perspective look kind of complicated, but there's a green one and a blue one, beta 1 and beta 2. So that's how we describe a 3-manifold. And now to that 3-manifold, we want to associate a larger dimensional geometric situation. So first of all, for the story, we also pick a base point which lies away from the alpha and beta curves. You can put it wherever you want. For example, you might put the base point W there. And now we want to associate to this data a higher dimensional object. The higher dimensional object is the G-fold symmetric product of the surface of genus G. So that is the space of unordered G tuples of points on sigma, and they're allowed to collide. So if you want to be very explicit, what you do is you take the G-fold Cartesian product. Oh, that's the wrong button. You take the G-fold Cartesian product of sigma with itself and divide out by the action of the symmetric group on G letters. So there's a beautiful, wait, what happened? Oh, what happened is I'm using the wrong button. Okay, that's good. Okay, so there's a beautiful low-dimensional accident, which is that the symmetric product, you're going to get symmetric product of an arbitrary space, but if you take a symmetric product of a 2-manifold, you can get a smooth, you get a symmetric product of a complex curve, you automatically get a smooth manifold. And this is an artifact of the fact that the symmetric product of the complex numbers is c to the n. The nth symmetric product of c is c to the n, and that's the fundamental theorem of algebra. A monic polynomial is determined by its unordered n-tuple of roots or its ordered n-tuple of coefficients. So this is the reason why the g-fold symmetric product is a smooth manifold. And this smooth manifold is now equipped with a pair of half-dimensional tori, g-dimensional. So it's a 2g real dimensional manifold. It's equipped with two g-dimensional tori, the alpha tori and the beta tori. So the alpha tori are simply those g-tuples of points where each point lives on a different alpha circle. And the beta torus is the analogous thing for betas. And okay, so here I remarked that the g-fold symmetric product is a symplectic manifold. It's in fact a smooth algebraic variety. And one can make these two tori to be Lagrangian submanifolds after work of Peretz. So now what is Heegaard Floer homology? Well, Heegaard Floer homology is this chain complex whose generators are the intersection points of the alphas with the betas. So very, very explicitly, a generator, a Heegaard Floer generator, is simply, oh, I keep pushing the wrong button, for goodness sakes, sorry. A Heegaard Floer state is a union over all elements of the symmetric group of a product of alpha I intersect beta of sigma of I. So these are the Heegaard states. And the differentials count holomorphic disks. So what's a holomorphic disk? It's a map from the standard disk with two mark points on its boundary. I think of a left arc and a right arc, which maps, oh dear, that's a little lag. Yeah, which maps the left arc into T alpha, the right arc into T beta, and it maps the two distinguished points to two Heegaard states. So you can look at these, that's a topological condition, but if you choose a complex structure on the g-fold symmetric product, you can ask for disks that are holomorphic. And now, we now can define a chain complex defined over a polynomial algebra in a formal variable u. So f to me is the field with two elements. I take f of u and this polynomial algebra in u, and I define a differential which is just to count. The differential of a Heegaard state is the sum over all other Heegaard states over a sum of all homotopy classes of these Whitney disks times the number of elements in the moduli space of holomorphic Whitney disks divided out by parameterization times y together with the u variable keeps track of the intersection number of the disk with a complex codimension 1 subvariety in the g-fold symmetric product, which consists of that distinguished point w times sim g minus 1 of sigma. Okay, so that's in a nutshell the Heegaard Floer differential. This is what one uses to define Heegaard Floer homology. And there are some simplifications you can do, which is, for example, you could set u equal to 0. You can invert u. There are various constructions you can take. I'll talk more about the case where you can set u equal to 0. Okay, so that's the differential. Here's an example. So for the Heegaard diagram that I drew, there's this curve alpha 1 intersects beta 1 in 3 points, which were labeled x1, x2, x3. You can see them. Sorry, this is some kind of virtual reality exercise. There's x1, x2, and x3, and so alpha 1 intersects beta 1 in the 3 points, beta 1 intersects alpha 2 in these 3 points, and so on. So we get a little matrix of points. And if you like, the Heegaard states are like the determinant of that matrix. So there are 18 Heegaard states, which are the products of the xi's with the yj's or the pi's with the qj's. So these are the Heegaard states. And now there's the miracle of nature. The miracle of nature is that what I described so far is a chain complex, d squared equals 0. And that is part of Lagrangian Floer homology. This is a special case of Lagrangian Floer homology that was introduced by Andreas Floer in 1988. And so we get a chain complex, we can take its homology, and fortunately, that homology group doesn't depend on the Heegaard diagram that you do to define your three-manifold. It actually depends only on the three-manifold. Is there a question? Did I tell you where the base point is? Somewhere. The story of the base point? We'll come back. Oh, we'll come back to the story of the base point. Sorry. Okay. So when the Heegaard diagram represents the three-sphere, for example, the invariant is very simple. It's just a polynomial algebra in U. So I want to tell a different story, and that is just there was a parallel story in Seiberg-Witten theory, which is that Floer, first of all, in Donaldson theory, defined a different version of Floer homology, which is associated to anti-self-dual equations, and called the instanton Floer homology. So soon after the Seiberg-Witten equations were introduced, it was clear that the same program ought to be able to be set up for Seiberg-Witten theory, but all the details, actually, the details of the instanton story were also not fully developed. Peter Kornheimer and Tom Rufka wrote this amazing foundational text in which they worked out all of Seiberg-Witten theory for Seiberg-Witten Floer homology for three manifolds. And they conjectured that their construction was isomorphic to the constructions of Heegaard Floer homology. And these conjectures were verified later by work of Kutluhan, Lee, and Taubes, and Kolan, Gigini, and Honda via some intermediate steps that were provided by foundational work of Taubes and foundational work of Hutchings and Taubes. Is that good? Okay, sorry. Okay. The old one, let's say. Okay, great. So, all right. So, are there any other questions? So, I just pretended to define Heegaard Floer homology. So let me, what's a panorama talk? I guess part of it I could go through and kind of list the greatest hits of Heegaard Floer homology. I started doing that, and then I ended after one. So if I had to pick one, let me say what that is. So if you have a three-manifold with torus boundary, there's what we can call the Floer exact triangle. So there are three manifolds that you can consider. You have a three-manifold with a torus boundary, and the torus, of course, is the hexagon with opposite edge identifications on it. And as such, there are three obvious curves that you can draw which pairwise intersect each other once. And I'm going to call them beta, gamma, and delta. And you can form three different three-manifolds by filling those three different curves. And that's something we call a triangle. And one of the first theorems that we proved is that Heegaard Floer homology satisfies an exact triangle that relates the Heegaard Floer homology groups of these three manifolds. And so this was inspired by an exact triangle that Floer had envisioned for instanton Floer homology. And a little bit later, Peter Kornheimer, Tom Rufka, me, and Zoltan also worked out an analogous exact triangle in monopole Floer homology. So let me give some examples. So one example is, suppose you have a knot in the three-sphere and you draw a picture of its projection. You can look at your favorite intersection point, and you can form two other links by what are called resolutions. You replace that intersection point with a non-intersection point like this or a non-intersection point like that. And special case of the exact triangle is that if you have a link in the three-sphere, there's a naturally associated closed three-manifold, which is called the branch double cover of that link. It's a three-manifold which maps 2 to 1 to the S3, except along the knot itself, where it's a 1-to-1 map. And a special case is that these three manifolds enjoy these three double covers enjoy an exact triangle. So this was, we noticed this, and what was kind of amazing was that just around the time, a few years earlier maybe, Chovanov defined a knot invariant, which also satisfies the same exact triangle, and which agrees with the Heegaard Floer homology of the branch double cover if you take a unlink. So I thought, well, that must mean that the two theories are isomorphic. That was youthful naivete. But what is true if you iterate the exact triangle is that there's a spectral sequence which starts off at Chovanov homology and converges the Heegaard Floer homology of the branch double cover. So this was a very nice bringing together of two apparently disparate stories from the day. Okay, so that was me telling the definition of Heegaard Floer homology and then listing some of my favorite theorems. There were many others, but I don't want to, I'll give an apology about that. But let me now raise some questions. So an obvious question is there some axiomatic characterization of Heegaard Floer homology? Or if you want to just be a little weaker, how many different three manifolds can you construct that satisfy the analog of Floer's exact triangle? These are hard to find, and any you have is guaranteed to be interesting. So, you could construct them using Lagrangian Floer homology, you can construct them using gauge theory. Maybe you can construct them by pure thought or by, methods from number theory. But whatever you get is pretty much guaranteed to be an interesting theory. Another question, which is sort of obvious that comes up, which is what is the relationship between classical three-manifold topology and Floer homology? So Floer homology is this new story. I'm talking about Heegaard Floer homology, but there are other versions of Floer homology. One could ask, what is the relationship between those and classical three-manifold topology? So I'm going to zero in on this in a moment. So one obvious question is, can you describe Heegaard Floer homology explicitly from the fundamental group of the three-manifold? And I think, well, I can't. I don't know. That would be very interesting to do. Okay, so now maybe I'm coming back to the story of the base point. You can set u equal to 0, which means that now we're counting holomorphic disks that do not cross the base point. And this is a theory which is good enough for many applications, but not good enough for everything. It's good enough for three-dimensional applications, but can't be used for four-dimensional, or is less useful for four-dimensional applications. But there was this wonderful moment in 2005 where Sucharit-Sharkar introduced this idea that you could look at Heegaard diagrams that are so complicated that there's all the interesting bits of the Heegaard diagram are concentrated in a single polygon, a very large, very many-sided polygon. And away from that, the curves cut the Heegaard surface up into bigons and rectangles. And we don't know what to do with the polygon, so you just put the base point right in there. And then you only need to count holomorphic curves that cover the region that's tiled by bigons and squares. And he found that for such a diagram, one has a completely combinatorial description of Heegaard, of the hat complex. So Sucharit and Jiajun Wang constructed such Heegaard diagrams for any three-manifold, and therefore rendered HF hat to be combinatorial. Okay, so having introduced HF hat, let me just go back to another kind of, to fleshing out a little more the relationship between, sort of questions about the relationship between the fundamental group and Floer homology. And the way to formulate, there's a nice formulation, which is to take the simplest three manifolds you can imagine from the point of view of Floer homology. So look at those Floer homologies. It's an easy computation that the total dimension of the Heegaard Floer homology is bounded below by the number of elements in the first homology in the three manifold. So by the way, I'm looking here at a three manifold whose first homology is finite. So you count how many elements there are in that, and the statement is that that gives you a lower bound on the dimension of the Heegaard Floer homology, because in fact, that number is the Euler characteristic. So the question is, for three manifolds for which that lower bound is sharp, those are sort of the Floer homologically simplest enough three manifolds. What can you say about these spaces? We called them L spaces, and one thing that there is there's a machine for constructing them. So the minute you have a knot in the three sphere, and you know that some surgery gives you an L space, then anything larger gives you, any larger surgery gives you an L space. So these are kind of, they're rare, but not so rare. And one can ask, what can you say about the topology of L spaces? Maybe, I don't think I wrote it on the slide. Another source of L spaces, if you take an alternating link diagram, a connected alternating link in S3, and you look at its branch double cover, that's also an L space. So those are examples of L spaces that are not necessarily lens spaces. And so here, I want to just state a question from the time, which is still open and has and received a lot of attention, but is, I think, a very interesting question that one should try to understand better. This was conjectured by Boyer, Gordon, and Watson, that for any irreducible rational homology sphere, the following three conditions are equivalent. One is that the three manifold is an L space. That's a Floer homology condition. The second is that the fundamental group is not left orderable. So a left ordering on a group is just a relation, x is less than y, and which is right invariant. So when if x is less than y, then you want x times g is less than y times g. So, so the conjecture states that a group is that Y is an L space if and only if the fundamental group is not left orderable, and the third condition is some geometric condition that says that it has no coorientable tot foliation. So foliation theory was introduced by Thurston and Gabai as a tool for studying three-manifold topology. So this is the sort of quintessential theorem that tries to tie in, or conjecture that ties together Floer homology with more classical objects in three-manifold topology. Okay, so and now this is my apology slide. It used to say apology on the top, but then I couldn't fit everything onto the slide. So there are many things that if I'd continued in the above realm, I would have run out the clock stating theorems by various people and conjectures. And now instead, I'm going to just apologize for the things I'm not saying. There were the reproofs of various gauge theory theorems, four-dimensional gauge theory theorems that we were able to do using Heegaard Floer homology. I will also, in this talk, quite oxymoronically, not discuss not Floer homology, which was constructed with Zoltan and independently discovered by Jake Rasmussen. And there were further dramatic and beautiful topological applications of not Floer homology, which I'm not speaking about, by Paolo Gigini, Yini, and Andras Juhas, and then later also in a different direction by Jen Hong. And I'm also not going to talk about computations of not Floer homology, including grid diagrams, which were including joint work with Ciprian, Manolescu, and Shuchait, and then later surgery descriptions due to Ciprian and some with Thurston. And the other thing I'm not going to talk about are the bordered not Floer homology computations, which are joint work with Zoltan. And finally, there's like yesterday, sort of the contact geometric applications of the story, starting with the contact invariant, which was inspired by a work of Kronheimer, Mruvka, and gauge theory, which we defined with Zoltan. It was okay. So maybe I'll tell a little story. We were in the midst of Heegaard Floer homology. We were to see what can Heegaard Floer homology do that what can Heegaard Floer homology do everything that gauge theory can? Was a question we asked, and the answer is no. But it can do many of the things that gauge theory can. The one thing that I thought we would never be able to touch was contact structures, because those are fundamentally geometric. How could we ever possibly say? How could Heegaard Floer homology ever say anything about that? So we went to this conference in Oberwolfach, and Giraud gave this beautiful correspondence between open book decompositions and contact structure, equivalence class of open book decompositions and contact structures, and that was when it became just clear that we would be able to define this contact invariant as well. So the contact invariant had many applications, pioneered by Paolo Liska and András Stipschitz and Honda Kazez and Matic, but I can't talk about them because I don't have enough time. And then there were invariants for Legendre and transverse knots by Zoltan, and later with Dylan and Paolo Liska and Stipschitz and Sobol. Okay, so that's one portion of the Panorama talk. So this is now, are there any questions? Yeah, it feels like I'm lecturing in a museum. It's like beautiful. There's oil paintings. But usually, you know, as anyone who knows me, my style is to pace around and elicit conversations from the audience, which I guess is a little daunting in this forum. Are there any questions? Okay. Yes?
What is something you would like to occur homology?
What's that?
What is something that gauge theory can do?
Well, there's kind of theorems about surfaces of general type. The Donaldson invariance of surface of general type is very simple. I don't know how you would prove that using Heegaard Floer homology. You'd have to understand what surfaces of general type, what their Lefschetz vibrations look like always. That's a place. Another place is things about metrics. You know, there are theorems about positive curvature metric implies that the Seiberg-Witten invariant vanishes, and I mean that's not something I know how to describe using Heegaard diagrams. Any other questions? Okay, so I want to now switch a little bit and talk about some of the things that I've been thinking about recently. So I'm going to first give a kind of really vague overview, and then I'll try to spiral in a little bit. But so I want to talk about bordered Floer homology. So bordered Floer homology is an attempt to kind of break down Heegaard Floer homology one dimension lower. So what would happen if you wanted to break up a three-manifold into its constituent pieces and compute invariants associated with those pieces to then glue together to get your actual three-manifold invariant. So the bordered Floer homology package would associate to a surface a kind of algebra. Let's say to a surface equipped with some data, an algebra. So with the data associated to the surface, let me just say is, let's say, a Handel decomposition. Handel decomposition of a surface, and we would like to associate to that, let's say, a differential graded algebra. So I'm gonna backpedal on that, but for the time being, you can just think of differential graded algebras. And so we'd like to associate an algebra to a surface, and if you have a three-manifold with bordered boundary, which means that you have your three-manifold equipped with a diffeomorphism that identifies its boundary with the surface described by a given handle decomposition, then to that you associate a module over this algebra. And similarly, if you have a three-manifold which is bordered by the same surface but within an orientation reversing way, then to that you would associate a kind of left module. So earlier we had a right module, now we have a left module. And what you want now is some sort of technique for building up the Heegaard Floer homology of the glued up manifold in terms of those two modules. So let's say you have a three-manifold that's cut in two along a dividing surface, then you want to say that some kind of tensor product of the two modules over the algebra should be what recaptures for you the invariant of the three-manifold. So this is a way to at least start to try to pick apart three-manifolds. So the first question you might ask was that in order to glue, so I said bordered, which meant that I had a three-manifold with boundary and I specified a homeomorphism from a given surface to that boundary. That's the data that you need in order to be able to glue two such creatures together. If I just have a surface, a three-manifold whose boundary is homeomorphic to a surface, and I have another one, I don't know how to glue them because I don't have the actual identification. But if I have identifications with some fixed surface, then I know how to glue. So the first question that you might ask then is, how does the invariant depend on the parameterization? And the answer should be that if you have a homeomorphism between two surfaces defined by two different handle structures, then there should be a bimodule associated to that data with the property that, that the invariant of this bordered three-manifold tensored with this bimodule gives you the invariant of the same three-manifold with boundary, only now the parameterization is twisted by a given homeomorphism. Yes? What is F? Okay. The question is, what is F? It's okay, you don't need, I can amplify it. So to me, Z is a handle decomposition. F of Z is the surface described by that handle decomposition. Okay, it was a little notational thing. Okay. Any other questions? So in particular, if you have two different surface homeomorphisms and you compose them, then you expect that the bimodule associated to their composition should be the tensor product of the two component homeomorphisms. And this outline should give a computation of Heegaard Floer homology, a sort of an algorithm for computing Heegaard Floer homology as follows. You take your three-manifold, you give it a Heegaard diagram, or a Heegaard decomposition. That means that you've got two very standard-looking surfaces with boundary, three-manifolds with boundary, and they're glued along some possibly interesting homeomorphism. And now what you should do is you factor your homeomorphism into a product of standard pieces. So the mapping class group is generated by Dane twists. Maybe you take your mapping class, you write it as a product of Dane twists. You associate the modules to each of those Dane, you have to do some model computations of the bimodules of each Dane twist. You tensor those bimodules together, you tensor them with the two invariants of the two sides, and that's what gives you the Floer homology of your three-manifold. So this is a conceptual framework for computing Heegaard Floer homology, as well as a conceptual framework for understanding the theory. Okay, now, it's still not built, and back in 2008, Robert Lipschitz, Dylan Thurston, and I worked this out for the U=0 specialization. And in fact, we worked out all of the above details. So we defined the algebras associated. Do I have a, sorry. We defined the actual algebras associated to surfaces. They're differential graded algebras. They're reasonable, friendly looking. And we computed the bimodules of Dane twists, and we used that to implement a computation of HF hat, which is more efficient than the Sharkar-Wang nice diagrams approach. It can be implemented, can actually do some real computations. But it's not the full answer, so we would like to understand HF minus. And I remember we were in Berkeley, I think 2010, and we sort of understood how this should work for HF minus as well, but there were a lot of details. So I said, listen, why don't we just write down the easiest case of the torus and then generalize it. Unfortunately, we're still here today. But I'd like to say more than I would have said then about the case of the torus, and maybe even promise that maybe within 2026 there might even be a preprint. So let me just tell you how this should work for torus boundary. And before I do that, I should apologize once again. There are other approaches. There's a geometric picture that's was developed by Hanselman and building on work with Rasmussen and Watson. I think that Adam Levine will be talking about that. There's an algebraic approach which gives a completely different algebra, which was discovered and worked out by Ian Zemke. And I won't attempt to. So a real panorama talk would have explained all of those constructions, and this is where I fall short. Instead of failing to do that, I will probably fail to describe what we did for the case of the torus, but I'll give it a shot. Okay, so what are the algebraic players in the story? So you want to associate an algebra to the torus, but it's in fact not going to be an algebra. So to start, what is an algebra? So a differential graded algebra is a vector space with a differential and a multiplication law, which I'm going to draw in terms of these trees. So there's this node here that corresponds to differentiation, and that node, that trivalent node, corresponds to multiplication. In comes A, in comes B, out goes A times B. So there are various relations that a differential algebra has. One is that D is a differential, so D squared equals 0. That means that if I've got an edge with 2 dots on it, that should be 0. Another is the Leibniz rule, which is the sum of these 3 trees is 0. And the third rule is associativity, which says that the result of this tree is the same as the result of this tree. So again, I apologize. I'm working with mod 2 coefficients. In real life, there are some interesting signs that come in with the gradings, but I'm suppressing all the signs. So I apologize. So let me give an example, which is relevant to us. This is the example of the torus. So I want to define a differential graded algebra, but the differential will be 0. So this is just simply going to be an associative algebra. And the associative algebra is associated to this quiver. So I'm going to draw 2 dots, apparently a blue dot and a red dot, and I have the 4 edges between them. There's something called row 1, which goes from blue to red, row 2 that goes from red to blue, row 3, and row 4. And what I want to look at are paths in this quiver, which means that I pick one of those 2 dots, and I look at paths that go ping-ponging between the 2 different dots, and they end up somewhere. Except I divide out by the following thing. I divide out by row I plus 1 times row I equals 0. So that is just a way of saying is that when I go from blue to red, then when I go back from red to blue, I have to be going by the cyclically next path. So I go here by row 1, then I have to come back by row 2. And then I go back by row 3, then I go back by row 4, then maybe back by row 1, and then eventually I just get tired of it and I stop. So these are the words. The words are then just sequences of increasing numbers between mod 4. Okay, increasing by 1 numbers. Okay, clear enough? Okay. All right, so here I said that again. So that's an algebra, but I want to now define an A-infinity algebra. But before I define the A-infinity algebra, I should just pretend to say what an A-infinity algebra is. So an A-infinity algebra is a generalization of a differential graded algebra where we now, there's a hand up here, okay, where now we had differential multiplication, now we have a triple multiplication, quadruple multiplication, and so on. And they satisfy what are called the A-infinity relations, which are, the first one is d squared equals 0. The second one is this Leibniz rule. The Leibniz rule, yeah. The third one is almost associativity, homotopy associativity. There are now 3 additional terms, and so on. So there are infinitely many compatibility relations that you have for an A-infinity algebra. And where does the A-infinity algebra come from? The A-infinity algebra naturally comes from a geometric object called the associahedron. This was discovered by Stasheff in the 70s, I think. But you can think of it as the compactification of the disk with n inputs and 1 output, or the disk with n plus 1 cyclically ordered points on its no, not cyclically, it's n plus 1 ordered points on its boundary, modulo conformal rescaling. So if I have, just think about the standard disk. I have one special marked point on its boundary that I think of as the output. So if you like, you could just think of the lower half plane with now 3 points on it, modulo conformal rescalings. Well, the conformal modulus of 3 points on the boundary of the lower half plane is just an interval. So what can happen is these 2 points can come really close to each other in connection with the cross ratio. So these 2 points could start to come closer and closer to each other, leaving behind that point, and then you get this kind of bunny in the compactification where I have a disk that bubbled off from my disk that has 2 points on it. Or maybe instead, these 2 points come together and you have the mirror bunny. So this is the simplest non-trivial case. Here's a more interesting case with 4 inputs. The 4-input associated, we have now 4 marked points on the boundary of the upper half plane, and we can have codimension 1 degenerations, which correspond to these 5 edges, which are marked by bubble trees of pairs of disks. Oh dear, sorry. And then there are the codimension 2 degenerations, which are configurations of triples of disks. So, by the way, there's a nice, if you like, this is a space. It's a space that has a CW complex structure. The cells in that CW complex are indexed by planar trees, planar rooted trees. And for example, the top cell is just represented by what's called the corolla. It's just got a single internal vertex, n inputs and 1 output. The codimension 1 boundaries correspond to have pairs of internal vertices. Codimension 2 boundaries, strata correspond to 3 vertices, and so on. And the boundary map takes a planar tree and looks at the sum of all the different ways you can attack any given vertex and insert an edge. So that gives you a chain complex, and somehow, like, those chain complexes are precisely the things that govern A-infinity algebras. So let me give it a basic example. So there's the torus A-infinity algebra, which corresponds to all the different coverings, or how should I say this? All the different maps of the standard unit disk onto the torus with 2 curves, with these 2 curves distinguished. And I want maps of the disk onto that torus, which map the boundary to the union of those 2 curves. and which have no internal branching at all. So they're covering local covering spaces. All of the interesting branching happens along the boundary. So I want to look at the space of such things, and that I claim can be organized into an A-infinity algebra. So, for example, here's an example where we might cover the torus with multiplicity 4. Then that looks like the torus I think of as having this tile, this basic tile, and what we're looking at are the different ways of I got 4 tiles and I want to glue them together, and that specifies a map then from the standard disk, which I think is this union of tiles, onto the torus. So, so I just draw this planar picture. So how did I get the planar picture? I took the previous picture and I looked at the universal cover of the torus on the right. That gives you just a plane with a bunch of horizontal lines and a bunch of vertical lines. Yeah, I can't do PDF files. Sorry. So and so now we're just if you lift the disk, that's going to give you some picture mapping into this covering space. So so here I've drawn a portion of that for this particular tiling, and now I just mark a point, which is where the top point in the disk goes, and as I go around, I read off which numbers I see. So here I go. I'm reading off. I see 3, 4, 3, 2, 1, 2, 3, 2, 1, 4, 1, 2, 1, 4, 3, 4. And I just declare that to be a higher operation with the inputs as specified over there. So another kind of nice way of encoding this geometric object is to think, rather than the tiling, to think about its dual tiling, which is going to give you a planar graph as below. Okay, so the A-infinity relations are then realized by looking at one-dimensional moduli spaces of, if you like, holomorphic maps from the disk to the torus. So you imagine that maybe if I insert a cut between this chord 1 and 2, then I have a one-dimensional moduli space. One of its degenerations happens when I cut all the way through there, and the other degeneration happens when I cut length 0. And those correspond to these 2 different trees. So this is a sort of geometric way of seeing the A-infinity relations. Okay, so we have to beef up the algebra. We don't have an A-infinity algebra. We have what's called a weighted A-infinity algebra. For a weighted A-infinity algebra, you have not just trees, planar trees, but you have planar trees together with a weight associated to each vertex, which is some integer. And so here's an example. I draw, this is an example, where I draw this tree with 2 inputs and a weight 1 on it. And I look at all of its boundaries, or all the different ways that I can insert an edge. So I draw the pictures that I have on the right here, all the different ways of inserting an edge there. So there's a geometric way of thinking about what I've done, which is, like I talked about the associahedron, which is this classical object. There's a similar CW complex that Robert and Dylan and I were studying. It's called the associaplex. The associaplex is n ordered points on the boundary of the disk, and then a bunch of additional points that can live in the interior of the disk. And the ones in the interior of the disk, for those of you who are familiar, there's a notion of a Deligne-Mumford compactification where the points are never allowed to collide, but the interior points I'm allowing to collide, so I'm not going to scale out there. So what I'm somehow doing is I'm taking a quotient of the Deligne-Mumford compactification, where I'm looking at the symmetric product of the interior of the disk, but I'm compactifying so that the points on the boundary remain distinct. So I don't know how clear that was. The picture you're supposed to have is that here I've got 2 points on the boundary of the disk, 1 point in the interior. The point in the interior can try to wander out to the boundary, and it can do it in various ways. It could, say, go just out up to here, and that's going to correspond to this degeneration. Or maybe it goes out and attacks this chord, and that'll correspond to this kind of end. There are all the 7 other or 5 other pictures that happens. Okay, so like I said, I don't know how to give a PDF talk. So I even forgot how to use Beamer. So I got some AI assistance. I asked the Claude to produce for me Beamer templates, and I kept adding slides until I was content that I had an hour-and-a-half talk. So, because I didn't want to be in that embarrassing situation where after 45 minutes you're done. So instead, I'm in the embarrassing situation when after almost an hour, I still have another half an hour's worth of slides. So I will hang on. I will go back. There's a beautiful story, and I will be more than happy to talk to you about it after the lecture. But maybe I should say some future directions. So before I do that, I should say, what am I claiming? I claim that we have the algebra associated to a torus. That's already written down. We have modules associated three manifolds with boundary. And we have a notion of a tensor product so that we have what you would want to have a pairing theorem. So a way of, I've got two three manifolds with torus boundary and you glue them together along the boundary, then the HF minus of the glued up three manifold can be described as a suitable tensor product of the two factors. So that's what I would have claimed in that additional half an hour. But there are some obvious future directions. One is to work out this story for genus bigger than one. Another is to understand what the bimodules are for mapping classes. And that would give then probably a reasonably effective algorithm for computing HF minus for three manifolds, and maybe even for understanding the cobordism maps. There are other problems. There's the problem of working out an analogous bordered algebras to efficiently compute knot-Floer homology. Zoltan and I did that for some specializations of knot-Floer homology. Presumably one should be able to do it for the unspecialized versions. Another more open-ended problem would be to try to tweak the constructions to come up with other bordered theories to construct other three-manifold invariants. And so those were my forward-looking, that was my forward-looking slide. And finally, I want to thank Claude for typesetting assistance. So there's a picture of Claude helping me typeset my document. Claude produced that, of course. And for some reason, my slides seem to be about the Riemann hypothesis. I'm not sure why. But anyways, so I want to thank you all for your attention, köszönöm, and I want to wish a happy birthday to whoever happens to have a birthday divisible by many small primes, and many more to follow. Okay.
Thank you, Peter, for the fascinating talk. Are there any questions?
So I have two. I have two questions. First of all, on the fundamental group, Poincaré's original idea was to prove the Poincaré conjecture by looking at the alpha curves and beta curves and somehow using the simple connectivity hypothesis to prove you could do the moves to make everything standard. You now have a lot more information about alpha curves and beta curves, and you hinted that there was relations to the fundamental group. You get to Seiberg-Witten theory, if you can get all the way to Donaldson, then you do have a relationship with the fundamental group. So I just wonder, is there any hope of actually giving a Heegaard Floer homology topological proof of the Poincaré conjecture? That's question one.
That would be great. Yeah. I don't have any idea. I think if I had ideas, that would be a different talk that I would have given. But that's, I mean, that would be great to see if one could understand that.
Second question. Both in physics and via Jacob Lurie, we have this idea that you shouldn't look just at, if you want invariance of 4 manifolds, you should have vector spaces associated with 3 manifolds and other algebraic objects associated with 2 and 1. And if you can even get all the way down to 0 with some good axioms, and Jacob tells you exactly what you have. Well, I don't think those axioms are going to apply to you, but what about pushing? You've gone down now.
There is some work of Manolescu and Douglas and I think also Lipschitz about cornered Floer homology, trying to associate something to a circle. Now, I think that story only works for the hat theory so far. So, I mean, that seems like another very promising direction to try to work out what minus thing you would want to associate to the circle, and I don't have any idea of what you would be associating to points, but yeah, that would be great to understand.
So I wonder if you'd be willing to cast your mind back to, say, 1997 and say why you thought, what were your thoughts about Seiberg-Witten theory that led you to think that this might be somehow related? Not that not a good idea, but just why?
So the hint, of course, was that the Seiberg-Witten equations on a Riemann surface are the vortex equations. So this was Taubes's PhD thesis, that the solutions I mean, he didn't say it that way, but if you look at R invariant solutions to R times sigma Seiberg-Witten monopoles, then that's identified with a symmetric product. That's true in any spin C structure except the one that bounds a handle body. So that makes it a little bit poetic. So for if you actually think about Seiberg-Witten equations on a handle decomposition, then the moduli space you would be looking at is the Jacobian with the theta divisor playing the role of like the non-smooth connections, the bad ones. But if you think about the Jacobian torus with the theta divisor as distinguished, that's a lot like the G-fold symmetric product with the G minus 1 first symmetric product distinguished. So that's a little bit of the poetry that went in that description. But I mean, if you're really honestly trying to do Seiberg-Witten theory, you would presumably want to understand this picture, and then you would try to understand. The solution Seiberg-Witten equations that extend over a handle body, those should form a Lagrangian in this. So, what are the natural Lagrangians in the G-fold symmetric product of sigma? Well, you know, there's one obvious one, which is the alpha tori. I, at the time, imagined that, you know, I just need to, like, channel my inner Tom Rivka a little more and just solve the Seiberg-Witten equations over a handle body. And it turns out that my inner Tom Rivka is just not that big. So, and then when Taubes came up with this amazing identification that goes through all this, you know, embedded contact homology and so on. At some point, I got up the courage to tell him that I imagined that one could try to solve the Seiberg-Witten equations on a handle body, and of course, that had occurred to him as well, but he didn't do it. So that made me feel a little better. But yeah, so there was guesswork, guessing what the Lagrangians ought to be. And there was a little philosophy at the time, which is that you find something new based on what you've seen before, and rather than you conjecture that they're equivalent, and then you move on. So this was like this bad example that was set to us by the Seiberg-Witten theory story. So we decided to continue in that vein, which is not to verify that these are conjecture, but not verify and just move on. And fortunately, that worked.
One more question. Anybody? If there are no other questions, let's thank Peter again. There is coffee downstairs, and we'll resume at 10:30 for the lightning talks. Surgery modules and immersed curves.
55 minutes? It's 55 minutes? Is that okay? All right, well, thank you for having me. It's really so great to be at this conference. So great to see all these graduate students who I haven't met yet. If this were actually a birthday conference, then I would say that, you know, at my second year of graduate school, I spent a lot of time reading conference dipshits, and during the summer of that year, I was giving my very first talk, and I thought it was just going to be a bunch of us graduate students at Columbia at that time, and I walk into the room, and Andras is sitting right in the room. But this isn't a birthday conference, so I'm not going to tell that story. Okay, so I want to talk about not Floer homology, bordered Floer homology, immersed curves and surgery modules. This is all joint work with Jonathan Hanselman and Ian Zemke. And Peter actually sort of hinted at where we were going with this. As Peter was explaining, bordered Floer homology is this incredible package of invariants for studying manifolds with boundary, and specifically in the torus boundary case, they've been doing this really amazing work on the minus version. And I want to give some other perspectives on this and explain how this is related to both the work of both of my collaborators and how we're tying this in. And I hope that to, in some sense, advertise some other perspectives here. Okay, great. So Peter didn't say that much about the link, the knot and link invariants of version of this, of Heegaard diagrams. But if you take 2 base points in a Heegaard diagram, then you can actually obtain not only a 3-manifold, but you obtain a knot sitting in there. And there's a more general notion where you can obtain links in the same manner. And basically, so for each pair of base points, you get a component. And Ozsvath and Sabo and Rasmussen simultaneously had the idea that you can extend, that you can get some other kind of chain complex. And the sort of language and the notation of this has changed over time, but we're going to be focused on really on knots. But when you have a knot, you get a chain complex over a 2-variable polynomial ring. What the names of the variables are have changed over time, but I'm going to use W and Z for the names of my 2 variables, and I'm going to use U to refer to the product of the 2 of those things. Just to give you an example, for the unknot, let's see how this pointer thing works. Right, so for the unknot, we're just going to, the very simplest example, you're just going to get a single copy of this 2-variable ring. For the trefoil knot, which I think I've drawn correctly down here, you get a chain complex with 3 generators. I've drawn them sort of geographically according to the grading conventions, which I will suppress, tell you some method of doing this. But you have 3 generators, and the differential of one of them is W times one generator plus Z times the other generator. So those are some examples. This has been a hugely useful invariant for all kinds of questions in knot theory, and we heard a few of those from our recent speakers. Okay, bordered Floer homology. Peter gave you a little overview of this. As associated to a surface, there's some kind of algebra. Associated to modules over the surface, associated to manifolds, 3 manifolds with boundary parameterized by that surface, you get some kind of fancy modules. These are quote unquote A infinity or type D modules. But it has this amazing gluing property, which is that you can compute if you have a 3-manifold that was obtained by taking 2 pieces and gluing them together, well, you can compute an invariant associated to one of those 2 pieces and invariant associated to the other of those 2 pieces, and then glue them up. And there's this pairing theorem that tells you that there's this funky kind of tensor product, this box tensor product, which is sort of a finite model for some kind of derived tensor product, which gives you the glued up thing. Okay, so this has been a very useful story. And one of the places where this has been a useful story, if you have, for instance, a knot sitting inside of one of your 2 pieces, then you can see how certain features of the knot Floer homology propagate. Okay, and we in fact just saw the idea of satellite knots. Well, what's the idea of a satellite knot? Well, you have a knot complement in S3, and you have a solid torus, and sitting in that solid torus, you have some kind of knot, and you glue them together, and the knot that was sitting inside of that solid torus becomes a new knot in S3, this kind of living in a tubular neighborhood of your original knot. And one of the things that, when we were all children, people like Jen Hom and I and various others were using this bordered Floer homology to compute invariance of satellite knots. And as Hugo said, you can see, there are many versions of this that you might want to obtain. All sorts of results in knot concordance have been obtained by especially using these satellite knots. It gives you this huge realm of things. Now, one of the things that you need in order to accomplish this is you want to understand how the bordered Floer homology of a knot complement in S3, that's one of your 2 pieces, you need to be able to really fully understand the bordered Floer homology of a knot complement. Okay? And then you do, for instance, one computation of the bordered thing associated to the pattern knot in the solid torus, and if you could understand all the bordered Floer homology of all knots in S3, let's say, maybe you could get some kind of structural results. And so, conveniently, I've actually told you, I'll give you some examples. So I'm giving you the hat version of this algebra. Peter told you the minus version, which had these 4 things. So if we're only interested in the hat version of the theory, we're going to have a puncture somewhere, puncture the base points, or set the u variable equal to 0. And so here's the algebra. This is the algebra associated to the torus. And so the bordered thing is like this. And if I give you a couple of examples, so what is the invariance associated to the complement of an unknot with a particular framing? Well, I've illustrated it over here. There's a single generator, and then the differential of that generator is the element rho 1, 2 times that thing. Okay, now you might want to say, well, is d squared 0? Well, yes, and that's true because by that relation that Peter described before, which I've indicated over here, that element squares to 0. And then similarly, if I give you the trefoil complement, I've drawn the CFD of that. Now you might notice that I've drawn this sort of geographically on the plane in a way that was somewhat similar to that complex that I drew on the previous page associated to the trefoil. And you might be wondering, is that a coincidence? And of course it's not. So one of the things that was proven in Lipschitz, Ozsvath, and Thurston's paper is that the knot Floer complex of a knot in S3 determines in a very systematic way the bordered Floer homology of the complement. Okay, so one of the things that, in fact, you don't need to know the whole complex. You really only need to know the WZ equals 0 specification. So what do I mean? So this is this complex over this 2-variable polynomial ring. I'm interested in the terms in the differential that have powers of W or powers of Z, but powers that of both can be set to equal to 0. This is, if you want to draw this graphically, this is you ignore the diagonal arrows, okay? And so they give us this very nice algorithm, and actually there's been a lot of work on this. It's really sort of a 2-way equivalence, and there was just a paper actually just recently by Sung-Kyun Kang and Gary Guth really elaborating on this correspondence in a much deeper way, and seeing why this is really sort of a two-way street. And there's really a clean recipe. In other words, what you do is, as long as you find certain bases for your complex that are nice and clean, and essentially, if you have a nice basis, if you have a horizontal arrow, which is to say a power of W, then you get some chain of generators in the bordered thing. If you get a vertical arrow, you get some chain of generators. And then there's one last bit to this, which is that you have to connect up. Here, I'll go back to my picture for the trefoil, right? So you have, you had one sort of horizontal chain, and that corresponds to the sort of horizontal bit of the differential. You have one sort of vertical chain, which corresponded to the vertical bit of the differential, and then you have to connect them up. And actually, the way that you do that depends somewhat on the framing. I'm going to suppress that, but the reason that you're able to do this is that there's essentially, because you're working with knots in S3, the Heegaard Floer homology of S3 is as simple as possible. It's just one generator. And that means essentially, if you think about the horizontal homology, the vertical homology, they're each one-dimensional, and there's basically one generator to connect up to one generator, and this works out very well. Okay, now I'll just mention, Peter alluded in his talk a few times to this bordered knot algebras story, which is some work that he and Zoltan did that provides this really incredible computational way of computing the CFKs of knots in S3. It doesn't compute the full CFK, but it computes this W equals 0 specification, specialization of that. And it can do it. It's built into Snappy thanks to Zoltan's code, and it can compute for 40, 50 crossing knots, instantaneously. It's really, really quite amazing. And very conveniently, that's exactly the level of specificity. I should say that Patricia, who just spoke, has these amazing ways of sort of going from there to then, at least in some cases, if I understand, actually extracts the full complex, which is a really great thing to be able to do. Okay, but the thing you might be wondering about is, does this CFK to CFD formula extend to the more general setting of knots in an arbitrary three-manifold? That is to say, for any three-manifold with torus boundary, you could think about it as the complement of a knot, right? And if I've told you the parametrization of the boundary, well, you think about, basically there's a longitude and a meridian there. Fill in the meridian, you have a closed three-manifold, and now you've really realized it as the complement of a knot, and I've told you what the meridian is, okay? And so is there a more general way of thinking about this? And this was a question I kind of have been interested in for a very long time. And so the theorem that Jonathan and Ian and I, one way of saying this is that yes, this is true, that the knot-Floer complex, together with something called the flip map, determines this complex, okay? Now, in some sense, this actually has already been known. Some version of this goes back a ways. There are these two papers by Iman Eftekhari, who is one of the organizers of this conference, a student of Zoltan, who, in these two amazing papers, one of which came out really sort of before there was even bordered Floer homology, you can extract from this. It's not really exactly stated this way, but you can extract some kind of description, a way of pulling the bordered out of not Floer homology ideas. But it gives you a sort of very non-reduced picture. It's a picture of the border that's very kind of hard to figure out. So we wanted to try to understand this in more modern ways and ways that will really sort of tap into a lot of more recent ideas. Okay, great. So before I do that, I'm going to tell you something about the surgery formula. So one of the things that I'm going to tell you about is a little bit about how not Floer homology tells you about surgeries, and some of Zemke's recent work on, which Peter alluded to in his talk, of another version of bordered Floer homology. In some sense, I sort of want to advertise this. I think this was actually the machinery that lies behind what Heegaard just spoke about in his talk, and I think this is a really amazing things, to make a very, very dated reference. Plastics, right? For young people, this is what you should learn about. Okay, but I have to tell you something about this idea of the flip map. Okay, so you have this this two-variable chain complex. And if you set one of the two and I said the two variables basically correspond to the two base points. So Peter told you how one of the base points in a Heegaard diagram gives you that u variable, okay? And if you have the second variable, we call the base points little lowercase w and lowercase z. If you and the corresponding variables are capital W and capital Z. If you set one of those variables equal to 1, that's like ignoring that base point, right? It's just like the contribution of that variable doesn't matter. If you set the other variable equal to 1, that's like ignoring the other base point, okay? And then invariance of Heegaard Floer homology tells you that there's some chain homotopy equivalence that comes from doing the Heegaard moves to take one base point to the other, and that gives you a homotopy equivalence between those two complexes. And so when the 3-manifold is S3, each of those two complexes is just, it's CF minus of the 3-sphere. Its homology is just one-dimensional. It's just F adjoin U. And so there's really only one way to identify those complexes. And so that's sort of, the flip map doesn't matter if you're thinking about knots in S3. But as soon as you get out of this world of knots in S3, all bets are off. Okay. And these subtleties of this flip map have tripped up a lot of really great things over the years. These subtleties have gotten in the way. Now I want to present a sort of modern version of this as described in Ian Zemke's papers, which is a really useful way of thinking about this. Because I'm going to give you a sort of fancy high-level way of thinking about what the knot surgery formulas look like. So one of the early results that Peter and Zoltan proved about Heegaard Floer homology is that this knot Floer complex determines the Heegaard Floer homology of all surgeries on the knot. And one way of formulating that is going to be in the language that I'm now going to describe. And the notation has changed over the years, but it's not just a notational shift. It's really a very cool change of perspective, and that's what's going to give rise to this version of bordered Floer homology. And then in that language, I'm going to be able to tell you how we get back and forth between that and the original border. Okay, so here's something you could do. I said that one of the ways that the old way that we used to think about the flip map was what I just said, which is ignore one base point, ignore the other base point, which is to say set the corresponding variable equal to 1. If you want to be a little bit more precise, rather than set the variable equal to 1, you can invert it, okay? And somehow that's supposed to essentially have the same effect, but maybe with a little less loss of information. Okay, so rather than setting W equal to 1, you could say, take your chain complex and you could tensor it with, the ring F adjoint W, W inverse Z. Okay, and likewise you could do the same inverting the Z variable. Okay, now each of those sneakily can be understood as some kind of twisted Heegaard Floer invariant with some kind of twisted coefficients, which is something that's, yes, Paolo. I haven't told you. I haven't told you what this T is yet. Yeah, I think what I've said is correct. So you could set the you can think about each of these complexes when you do this inverting thing as some form of twisted Heegaard Floer homology where you've introduced a sort of an invertible variable. And sneakily, if you do that, there's a nice change of variables. In each of these, there's a way of doing that. In one of them, you change your ring to, I've told you U was W times Z and T was W inverse. And suddenly this flip map becomes a statement of the invariance of twisted Heegaard Floer homology. Now, why would you want to do that? One reason you can do this is you don't have to work with null homologous knots anymore. But this gives you another way of understanding what this flip map is. Okay, and now I can tell you in one line, in some sense, what is the what is this Heegaard Floer surgery formula? The way this identification, you need a framed, right? So you need a framed knot. But when you've done this, the framing only matters up to like an overall power. And you get these two inclusions. So what are the two inclusions? The inclusions, one are, I can take my chain complex. Let's just go back. I can take my CFK, and I can just directly include it into here, right, where I've just inverted my Z. And I can think about that as my, as a map, okay? And if you know the old version of the surgery formula, this thing is what we used to, the CFK is what we used to call the A complexes, and this twisted thing is what we call the B complexes. And if you do this, right, so you can just do a standard inclusion. Or, and we call that the V map, which stands for vertical for a reason that is maybe not at all clear from this picture. But then the other thing you could do is you could include it into here by inverting W, and then compose with this flip thing. And that's another map. So now I have basically two maps of the same space into there. And this miraculous mapping cone formula of Ozsvath and Szabo, reinterpreted in this language, tells me something about the Heegaard Floer homology of all surgeries. And the theorem says that if you want to compute surgeries of any Dane surgery, let's do integral Dane surgery on a knot in any three manifolds, you can obtain it in this way from the Floer homology. You have to do complete. You have to. I'll sweep under the rug the fact that you actually have to, allow for power series coefficients. But okay. And one of the things that's cool is that you can. This works when the knot is homologically non-trivial as well. It took me a while to sort of come around to this new notation for thinking about this, because if you learned how to do this in 2007 or so, like you learned one set of notation, and then but I really think this is a very great perspective. And okay, so now why am I telling you all of this? What Zemke does in this paper, which showed up so nicely in Hong Yi's talk, is you can think about these surgery modules, the structure of the surgery formula, as giving rise to a version of bordered Heegaard Floer homology, giving rise to an invariant associated to a framed knot. That's basically what I just had, right? Everything that I just described was associated to a knot and a framing on it. And if you prefer, you can think about that as a delete the knot, and now you can remember where the meridian is, and you can remember what the framing is. That's telling you a knot with its a three manifold with its boundary parametrized by a torus. Okay, and amazingly, that can be understood. That data, everything that I just wrote down, can be understood as a version of bordered Heegaard Floer homology. Okay, so maybe I'll tell you what the algebra is. It's sort of, it's quite different from the algebra that Peter was describing before. We're going to take an algebra. It's going to have two orthogonal idempotents in it. We'll call them I0 and I1. And they're basically corresponding to the two pieces of the surgery formula. So in one of those two idempotents, I'm going to take a copy of a two-variable polynomial ring. In the other, WZ, in the other one, I'm going to take a copy of this FUTT inverse. And then you're not going to have any, going from I1 to I0, you're not going to have any algebra elements that go in one direction between them. And then in the other direction, you're going to have these two elements called sigma and tau. Okay, we can think about this as an algebra. You can, so now it's got some polynomial, funky structure in it. And now if I give you a knot, we're going to think about some kind of type D module. So maybe I'll even say something about this. This is a really great algebraic perspective. Let's say you want to think about, if you want to think about chain complexes of free modules over a polynomial ring, let's say, right? So you could think about those kinds of objects. But there's a sort of cute algebraic way of repackaging those, which is known as type D modules. And the cute way of thinking about it is just take a finite dimensional vector space of the same dimension, right? With a basis corresponding to your original one. Okay, now in a free module over a polynomial ring, the differential is basically just a matrix of polynomials, right? The differential, the differential of one element is, a polynomial linear sum of the other things. We're just going to record those as, we're going to record that differential, that same data, as a map on this finite dimensional thing. So you should think about it as a map from this finite dimensional vector space to the finite dimensional vector space tensored with your polynomial ring. And you could do it on the left or the right. In this case, in polynomial ring, it doesn't matter. And this is sort of a nice little bookkeeping device for keeping track of the differentials while keeping sort of the underlying objects as being finite dimensional vector spaces. It seems like a sort of cute algebraic gadget, but it turns out that it's very useful, especially for the purposes of this box tensor product that I alluded to before. It's a good way of doing algebra. Okay, and it also works nicely when you have non-commutative rings as well, like the one that I've just described. Okay, so what is this ring going to be? What is this module? So what we're going to do is we're going to take our knot Floer complex, and the data, all of the data that went into the surgery formula, and we're just going to repackage it as a type D structure over that algebra that I described for you before. Okay, and this is what Zemke does, and this is the structure. So basically, in one idempotent, you've repackaged the knot Floer complex as a type D structure over FWZ. In the other idempotent, you take the twisted twisted invariant, and then basically the V and H maps are just corresponding to those two things. The exact details aren't so important here. But what's amazing is that there's a pairing theorem. And it's not just a pairing theorem for the hat version. It's a pairing theorem for the full minus version of this. So Zemke tells you exactly how to do this. So you can compute, if I give you any two knot complements, and I understand the CFKs of both of them, and if I understand the flip maps of both of them, then by tensoring those, by doing whatever this fancy A infinity tensor product, box tensor product in this category of modules is, you can compute HF minus of the glued up thing. So specifically, what are you doing? You're taking the two 3 manifolds, you're connect summing them together, you're connect summing the knots together, okay? And you're then doing surgery on that connect sum. And you can think about that surgery on the connect sum as, in other words, being you've glued together the complements of the knots, longitude to longitude, meridian to meridian. Okay, so this is a version of bordered Heegaard Floer homology, right? And it's a 3-manifold invariant. It's an invariant of 3 manifolds with torus boundary, and it has a pairing theorem that can compute HF minus. And by the way, there's a much more general version of this where you can do links as well. And if you want to do a gluing along one component of a link, you can do all of these things. So this is what goes into these great papers of Chen, Zemke, and Zhou, which do all of these, show how this can be used for satellite computations. All these kinds of satellite computations that, I used to break my teeth over when I was a graduate student or a postdoc. I really think that, especially for those kinds of things, this is a good story to understand. So, okay. So now the question you might be wondering is, how does this relate to the old version of this? And the answer is, we can translate between them. And the theorem, that is our new work, is that we have an explicit bimodule for translating back and forth between these two stories. And I've drawn it for you here. It's probably a little meaningless unless I tell you the notation, but those are the generators, those are the differentials. There's a completely explicit bimodule, which if I, so I called it B, and it's a bimodule. It's a left-left bimodule. It's type A action of Zemke's algebra K. It's a left action of the Lipschitz-Thurston algebra A. That's type D. That's this notation. I get it wrong every time, so don't worry about it too much. But it is actually, we've set up this module, and it is exactly such that if you take the Zemke bordered thing and you plug in this bimodule and you compute this tensor product, then what pops out is the original LOT version of ordered Floer homology. Okay? How do we compute this? Well, basically, we just needed to compute. You can extend Zemke's story to not only knots in closed three manifolds, but knots in bordered three manifolds. And it works quite well. And you can do, and there's some kind of, and essentially we just had to do one computation of that invariant associated to a solid torus and a knot, the core knot sitting in that solid torus. And there's a further statement you can make, which I won't go too far into, but that actually, you might be asking, well, is this actually truly an equivalence of categories, right? And the answer is no, and the reason that the answer is no is that there's a loss of information. So as Peter told us, right, the hat version of this theory, this is all the u equals 0, this simplified version that's very good for three-manifold applications, but not four-dimensional applications. Whereas this Zemke version is doing the full minus thing. So inevitably, basically, I've killed a variable along the lines as I've done this. So we have a loss. There's some loss of information in doing this. Nevertheless, it does give some kind of equivalence of categories between something and something else, which are precisely the places where these invariants live. So this is good. Why should you care about this theorem? One of the reasons you should care about this is if you wanted to do the kinds of computations that that we all used to do. For satellite knots, for instance, you can exactly obtain a version of the original of the CFK to CFD formula that looks a lot like, but with this extension, this extension without this requirement that you're only living in the world of S3. That's one reason you might want to be able to do this, and it really just comes from exactly from this structure. Another reason you might care about this is that using the Zemke pairing theorem, you can recover the pairing theorem from the original 2008 bordered Floer homology paper. Now, okay, it's great to say, well, you can recover new proofs of old things. If you're, scared of holomorphic combs or whatever I mean, there's some very, very difficult holomorphic analysis, I guess, in both of these settings. But one of the things that sort of is I mean, this whole paper is in progress, but this part we really fully understand. The idea that you might really wonder about is, can you do the same thing for the version of bordered Floer homology for minus that Peter was describing? And conceptually, we believe the answer is yes. We basically think the same template of proof is going to work to be able to give a way of saying that not Floer homology will determine the minus bordered invariant of the knot complement. The devil's in the details, and maybe 15 years from now we'll still be writing this paper up. But hopefully that's not the case. And I think that's sort of the proof schematic. I think it will work in the same way. So that's one of the reasons that you might care. Okay, I've blabbed a lot about this. Any questions so far? I have till 11:45. Is that 11:45? 45. Okay, great. Okay, now the second part of this story is about immersed curves, and this is another one of these great stories. And now I get to highlight both Hanselman and Jake Rasmussen and Liam Watson, both of whom are here. And this is this totally baffling story about immersed curves, which has been very influential and a really great tool. So around 10 years ago now, I think, Jonathan and Jake and Liam had this really remarkable idea, which when they told me about it, I was like, that's magic. That's not, which is a new way of thinking about these bordered Heegaard Floer invariants. Okay, and let's go back to the examples that I drew before. And so it's very, when you have these kinds of invariants, right, which I've drawn by basically a bunch of generators and a bunch of arrows between them. And there were two classes of generators corresponding to the two idempotents in the algebra, which I've drawn as sort of dots and solids. And they had this sort of ridiculous idea, which is like, let's draw this on a let's just draw these pictures like sitting neatly on a torus, okay? And basically we'll draw, so think about the torus as the square with sides identified, and we'll draw one of the classes of generators sitting along the vertical edges, and we'll draw the other kind of generators sitting along the horizontal edges. And then we'll just draw the arrows connecting them, sort of sitting neatly on that torus in some prescribed way, and depending on which kind of arrow it was, that they'll tell me which corner of the torus I drew it in. Okay, now, why would you? Okay, you could do that. But the absolutely incredible thing that comes out of this is that this has geometric meaning. Okay, and so if you have a what we call an extendable module, which is some kind of condition on the algebra, then it turns out that up to the right kind of change of basis, well, if I had just done this, and if in this picture here, I had more arrows, right? I mean, this picture, as I've drawn it here, was sort of very neatly drawn as a loop, right? Basically every vertex had exactly 2 incoming or outgoing arrows. And so what ended up happening here is that, the curve, the complex as drawn on this torus is just like a loop sitting there. But it turns out that somehow every complex that satisfies whatever this extendability condition is, actually up to change of basis can be put in some nice form. And so that you can actually turn the algebra of working with modules over this weird ring into a process of just drawing curves on a surface. Okay, and it seems kind of mind-blowing. Okay, and so I've done this in 2 examples, and if you notice, I've actually, on the right-hand side, you can lift this. Sometimes it's easier to picture this in a cover. So if you imagine unwinding each of those tori vertically, the thing that I've drawn on the right is what you actually see here. So that's just maybe a suggestive picture that makes it seem a little simpler. Okay, and so the theorem that they proved is that you can, if now you want to think about the bordered Floer homology of a 3-manifold, you can think about that as an immersed multicurve in a torus. Maybe with local systems, I won't tell you what that means. And now, a bordered 3-manifold with torus boundary has torus boundary. That was kind of tautological. So you might want to think of that torus boundary as being identified with the torus that we just drew, seemingly arbitrarily, right? And the magic is that that works. And that, so as Peter alluded before, right, we understand how these bordered invariants change under reparameterization. And the way that the immersed curves change under reparameterization turns out to be exactly doing those daintists on the surface. And so you can actually think about those curves as living somehow on the boundary of the 3-manifolds, punctured at a point. Okay, now that's great. Why would you want to do something like that? The thing that's really crazy is that if I want to do this gluing story, right? I want to take 2 3-manifolds and glue them together, okay? And I want to glue them by some homomorphisms of their boundaries, well, you could take the curve associated to one, and you could take the curve associated to the other, and you could plop them together on the same torus. And now I have two curves, a red curve and a blue curve, sitting on the same surface. There's a base point where we've punctured. And you could do the Floer homology machine, and you run the Floer homology machine, and it corresponds exactly to the box product differential, which I didn't even describe before. So all of the fancy algebra that went into bordered Floer homology can be encapsulated by this geometric structure. And this was, when I heard about this, my mind was completely blown. Okay, and you can use this, you can use this to prove all kinds of amazing things. I didn't state them here. One of the things that they proved in their original result is, for instance, if you have a three-manifold that contains an incompressible torus, right, that you've glued two things together that weren't solid tori, essentially, and you glue them together, then that thing cannot have Floer HF hat of rank 1. Or 2 or 3 or 4. It has to be at least 5. So this has been, they used this kind of machinery to understand a lot of things about the L-space conjecture. It's been a very useful tool for me as well. It has, in various sorts of computations in the recent work that I did some years ago, a couple years ago now, with Ty Lidman and Lisa Piccirillo. We did some of these alpha invariants that Lisa talked about in her talk. We had to do some computations of those for a certain family, and we were able to do some computations using this geometric picture that would have been a total nightmare to attempt to do sort of algebraically. You just kind of pull the curves tight and you count them, and it's a spectacular computational tool. Okay, so now that's all for the hat version of bordered Heegaard Floer homology. So then Jonathan Hanselman did something a few years later, which he said, well, okay, let's see if we could do this for not Floer homology as well. Let's see if we can encode not complexes in this picture. And indeed you can. And we'll do so, and I'm going to sort of maybe describe it a little bit more explicitly here. If you have, well, here's what we're going to do. If I give you a chain complex over the ring that we're interested in, we're going to figure out how to encode that as an immersed curve. Okay. If you want to do this, well, here's how we'll do it. There need to be some gradings in this story, so we'll assume that the gradings are what they should be. We're going to basically take an infinite vertical strip. You're going to put base points at the vertical half integer points. For every generator of the complex, we're going to put a little horizontal segment at the right height, at a height corresponding to some kind of grading. I've sort of tried to draw this here for you. And for every W power bit of the differential, I'm going to connect the corresponding generators with an arc on the right. And for every Z power generator, I'm going to connect them with an arc on the left. And if I do that with the complex that my trefoil complex that I've drawn over here, you can see exactly the thing that I have. Now, in general, I'm just going to have I'm going to have some kind of messy graph, but it turns out if you can find the right kind of basis, nice simplified basis like this, then you can find something that's just going to turn into, an arc. Now maybe it'll close, maybe it's going to close up, maybe there will be some ends hanging off the end, the ends that hang off correspond to the homology somehow. This is this method of encoding a complex as a curve. And so the left ends correspond to, in some sense, to the W equals 1 specification of this. The right ends, the homology of the W equals 1 specification. The right ends correspond to the homology of the Z equals 1 specification. And if you knew how to identify those things with each other, you could take that infinite strip and glue the sides together and connect the ends, and suddenly you have a closed curve in S3 cross in an infinite cylinder. Okay, and this is what Hanselman did a few years ago. He says if you you can encode this CFK minus story with an immersed multi-curve in an infinite cylinder, keeping track of some base points, possibly with some local systems. And in fact, you can even encode the full complex, and the full complex corresponds to some extra bit of data. It's something called the bounding cochain, and you know, this works. And so so I guess going back to my previous example, right, for the trefoil, right, we're just going to glue those ends together. Okay, now for knots in S3, one of the things that this, let's see. I just wanted to give you some picture to show off. This was something that came up in something I was thinking about. Why you should care about that knot, who knows? But this is an example of, I've drawn my chain complex, and this is an example where you actually need to pay attention to the bounding cochain for some reason. I left some version of a picture lying around my house one day and somehow got shared in our family group chat, and you know, and it's like this is what it looks like when Adam is working, and you know, there was a great deal of ribbing that went on. Okay, so one of the things that Jonathan can do with this, for instance, I explained that mapping cone formula to you, right? That mapping cone formula, as I said, well, I told you what the maps were, I told you what all the inclusions were, right? That was a bit of an algebraic mess. One of the things that comes out of this is that mapping cone formula admits this completely geometric description as well, which is the following. Take your immersed curve, it helps to sort of unwind it and put it in the plane. Take a line of slope P over Q, where P over Q is the surgery. Count the intersections. If you want to do just HF hat, count the intersections, and you get that. But if you want HF minus, you can do that too. Okay, so, and that's one of the things that Jonathan showed. So, okay, now you might be wondering, how does this relate to that? How does this immersed curves version of not Floer homology compare to the immersed curves version of bordered Floer homology that I told you about 10 minutes ago? I realize I'm, you know, sort of throwing a lot of different things at you, but you might think they might be related to each other in some way. And in the S3 setting, one of the things that Jonathan showed, and really by construction, is that the CFK to CFD formula, as done by Lipschitz, Ozsvath, and Thurston in the original version of this, right? If you remember going back to it, each of the W arrows corresponded to some collection of generators on the bordered side, and each of the other things correspond to some string of generators on the bordered side. And if you turn them together, those two curves actually exactly agree with each other by construction. Okay, but outside of the S3 setting, we don't have that luxury, precisely because the flip map business keeps screwing everything up, okay? And you don't know, I mean, you can still say that the complexes, you know, just at the level of complexes are the same, but you don't know how to glue them up. And if you want a curve in the torus, right, you're gonna have to figure out how to glue them going around the other side. And one of the things that we prove in our paper is that this works in general, okay? So what happens is that coming out of this bimodule story that I described, you get something, you get a surgery, a mapping cone type description of the bordered invariance. It really looks a lot like the mapping cone description of HF hat or of surgeries, but you get this mapping cone description. And as Jonathan's story said, you know, these immersed curve things are very well adapted to those kinds of things. And so really staring at you right in the immersed curve things, if you deform the curves in the right directions, then the connection between these two immersed curve stories just suddenly falls out of the picture in a rather remarkable way. We also, one of the things we actually tried to do earlier on, and it turns out to be less efficient, but it also sort of works, is that you can sort of describe, in these old papers of Eftekari, there's sort of some kind of description of bordered that comes out of that, and you can describe that sort of in an even further perturbed immersed curves language as well, but somehow this is, we ended up with a cleaner picture here. Okay, so just to tell you what's left, as you know, the next things to do with this is that you should be able to, number one, you should be able to describe Zemke's pairing theorem for HF minus, right? We've just said that I can get a pairing theorem for HF minus coming out of this new version of ordered Floer homology. I've just told you, in essence, that version of ordered Floer homology, well, is the same thing. It's the same data as the knot Floer complex and the flip map. Well, the knot Floer complex with a flip map, that's an immersed curve, so we should be able to write down, and I think I'm quite confident that that pairing theorem really can be expressed as an intersection homology of these curves. We should then also close that loop by saying that the new version of ordered Floer homology, that pairing theorem as well should also be expressible. I really suspect that all of the, you know, once I managed to work my way through the full bordered minus and really understand that, which I fully admit that I don't, we should be able to really understand that these theories are totally equivalent to each other, and that for different purposes, different approaches to this computation might be better. So I will leave it at that. Thanks for listening.
Right. Are there any questions for Adam?
So you said that the thing you've done with Ian and Jonathan, you basically killed one of the variables, and so that makes it not CFD minus. Can you say something about how, like, what would change with like the X, N, et cetera, bimodules to get to the minus case?
Yeah. Okay. So great. So the question is, what do you have to do for the minus case? Here's how we did this. Here's what that bimodule is. Let me go back. Okay, so I just wrote some mess there. But what is this bimodule? You could do, one of the things that you can do is, we're going to set up some setup. Let's say I have a knot in a bordered manifold. Okay, I have a bordered manifold, actually genus of any, boundary of any genus if you like. I have a knot sitting in that complex. You can write down a version of bordered knot Floer homology, a little different from how they do it in the original papers, a version of the bordered knot Floer complex of the knot in the three manifolds. And it turns out that you can do an integer surgery formula, a Mappigon surgery formula for knots in bordered manifolds. The story goes through really almost the same way as you would do for knots in closed manifolds. So if I have a knot in a bordered manifold, I get an invariant that is a type D structure over the algebra associated to that boundary, adjoining two variables WZ. Okay, and then you can basically run the exact same Mappigon surgery formula. And obtain a formula for the bordered invariant of the knot in the for the bordered invariant of the surgered manifolds. Okay, you can do that. I love the Latin phrase, mutatis mutandis, right? Like, just change, is the same thing as it was done before. Just, change all the details. Leave to the reader to change the details. Then the next step you can do is translate that into thinking about associated to a knot in a bordered manifold. Think about that as a bimodule over the LOT bordered algebra on the boundary side and the Zemke algebra on the not side, right? Which is encapsulating the same data. And there's a pairing theorem that works for basically, which is just a matter of sort of connect summing with that knot and doing surgery on it. Okay. So what we do in our paper is the bimodule that we compute is just that associated to take your 3 manifold to be a solid torus with the standard border structure on the outside, take the knot to be just the core circle, and just compute that. And we just explicitly compute that, and that's what this bimodule is. In principle, the same thing ought to work if instead of now doing this with hat bordered, we do it with minus bordered. And run the same strategy, and you got to compute one invariant associated to 1 knot and 1 3 manifolds, but that should be the bimodule, and okay, we got to convince ourselves we got to convince ourselves that mutatis mutandis actually is valid, which is probably a lot of pages of math, but that's the rough idea.
Any other questions?
So do you expect that the kind of minus version of the immersed curve story should involve just bounding cochains like in Jonathan's knot story, or should there be some other data that goes into it?
I would hope that it would just be bounded cochains, but I don't know well enough to. I would think. The invariants on the two sides are each bounding cochains, right? Each complex is encapsulated with a bounding cochain. But I'm sure there are things that could go wrong that I haven't quite anticipated.
So I had a specific example in mind, like if you take maybe just the solid torus and connect sum it with some rational homology sphere. How would you expect the invariant of that object to depend on HF minus of the rational homology sphere?
I will try to not answer that on the fly, but it's yeah.
Thanks.
So the map between the idempotents of x lambda are determined by the mapping cone?
Yeah, exactly. It's basically just a sort of funky algebraic repackaging of the mapping cone.
Is there a way to go backwards? Like if you really cared about the mapping cone, but you only had x lambda?
Yeah, you probably just basically you're just reading it essentially right off of that. Yeah.
Right. Maybe one more quick question.
Hey, I'm wondering if it would be possible for you to comment on, is there a status update that can be given about the status of functoriality for any of these theories?
Status of what?
Of functoriality.
Functoriality.
So partially worked out for the bordered, I think, but what about the surgery modules and the immersed curves?
The functoriality in the immersed curves is, I think, not really understood, or at least I'm not aware of that. The functoriality for the surgery modules is, I think, basically a consequence of the functoriality of knot-Floer homology. And if you understand the naturality of knot-Floer homology, then I guess you should get some version of functoriality there. But yeah, it's more or less the same idea, but I'm not sure anyone stated it carefully. I don't think that anyone stated it carefully. So.
Talk. And we'll resume at 12.
Okay.
Hi, everyone. Yes, welcome back to this last talk of this today, and I think also the first half of this conference. Okay. My name is Zhongtao Wu, and I was another student of Zoltan. And you might wonder why my academic brother, Andras, did not just carry on. Oh, he's here. Yeah. So the truth is that we have about 10 organizers, and we are all eager to have some stage time in this beautiful venue. And but we only have 8 sessions. So voila, I'm this extra pigeon, okay? So yeah, but without further delay, I'd like to introduce our next speaker, Jen Hom from Georgia Tech, and she will talk about both the exotic space and Heegaard Floer homology.
It's an honor and a pleasure to be here. When I was a graduate student, sort of 2 very formative texts for me were the lecture notes that came out of the Clay Summer School here in 2004 and Gompfen's Dipshits. All right, so today I'll be telling you about exotic R4s using Heegaard Floer homology. This is joint work with Sean Eli and Ty Lidman. So like a lot of talks this week, this sort of spans multiple themes. So, this spans sort of Monday and today. All right, so what am I going to tell you about? What do I want to talk about today? I want to talk about this sequence. Can someone tell me what this sequence is? Thank you, City. It's the number of smooth structures on Rn. Terrific. Okay, so there's sort of lots of, okay, so in dimensions besides 4, the story is not very interesting, so it's due to Moyes and Stallings. And then in dimension 4, as we heard on Monday from Danny, well, sort of, it really, it's based on work of Friedman and Donaldson, right? So Friedman giving us manifolds that are homeomorphic to R4, Donaldson showing that they're not diffeomorphic to R4. And then Bob showed that, in fact, well, there are infinitely many smooth structures on Rn. And in fact, well, Taubes did even better. Well, there's uncountably many smooth structures on Rn, on R4. OK. And so today I want to talk about some exotic R4s. What kinds of exotic R4s do I want to talk about? I want to talk about R4s built from a ribbon disk exterior together with a Casson handle. So first, I want to tell you about ribbon disk exteriors. So here's a knot. It's the pretzel knot P -3, 3, -3. I've drawn it in a way that hopefully you can see that it bounds a ribbon disk in S3. So here's the ribbon disk that it bounds. This is an immersed disk in the 3-sphere that only has ribbon singularities. So the ribbon singularities are here and here. Great, so this is going to be one of the building blocks for the exotic R4 that I want to build. All right. OK, and so we can think about S3 as being the boundary of the 4-ball. And so then this knot is sitting in S3. In S3, this disk is immersed. But because the only singularities on the disk are ribbon singularities, we can push this disk into the 4-ball, and then it becomes an embedded disk. So we have this embedded disk in the 4-ball. OK, and so this is one of the ingredients in our recipe. What do? We want the other ingredient is going to be a Casson handle. So a Casson handle is something that's homeomorphic but not diffeomorphic to D2 cross the interior of D2. In a few minutes, I'll say a little bit more about Casson handles, but for now, this is a sufficient way to think about it. OK, and so then the next step, well, let's remove a neighborhood of this ribbon disk. So we're cutting out a D2 cross D2. And then, well, let's replace that ribbon disk that we cut out with the Casson handle. And the last step is going to be, well, we'll delete the boundary. And so that's sort of telling us that how we're gluing in the Casson handle. So sort of the D2 direction is sort of the neighborhood direction, and the interior of D2 direction is sort of along the disk. Great. All right. So these are the manifolds that I'm going to be interested in today. Okay. And so, well, so far in this recipe, I just said do this with some ribbon knot in S3. Okay, well, what if you start with, say, the simplest ribbon knot, the unknot? Well, then it's the result of Friedman that, well, if you follow this recipe, what do you get back? The thing that you get back is in fact, just R4 standard. Okay, well, you might also be thinking, well, okay, the unknot has lots of ribbon disks. So I guess Friedman proved this for the unknot with its sort of simplest ribbon disk. But Gompf actually showed, well, pick any slice disk for your ribbon for the unknot, do this recipe, and then you're going to get R4 standard. However, well, if you do this with a more interesting knot, so for example, if you do this with the aforementioned -3, 3, -3 pretzel knot, then you do get an exotic R4. And this is a result due to Bichatza Gompf. All right, and so the question that I want to address today is, well, what is the effect of the knot that you use on the exotic R4? So in particular, well, if I put different slice knots into this recipe, do I get different exotic R4s? Okay, and so I'm standing up here today giving you a talk, so the answer, not surprisingly, to this question is yes. That's the main theorem for today. So this is joint with Sean and Ty. Okay, so I'm building my R4 as I described, so I'm attaching a Casson handle. If you already know about Casson handles, I'm using the simplest possible positive Casson handle. I'm going to attach this to a slice disk complement of a non-trivial slice knot in S3, and then remove the boundary. Okay. Well, as long as I started with a non-trivial slice knot, well, then I'm going to get out an exotic R4. And then, well, you also might ask, okay, well, if I use different slice knots, do I get different exotic R4s? Well, I'm standing here today on Heegaard Floer Day, and so basically the answer is, well, as long as the knot flow homology of the slice knots that you're using are sufficiently different, well, then you're going to get distinct R4s. And so for the knot flow experts in the audience, what do I mean by sufficiently different knot flow homology? Well, look at HFK hat of your knot, and then we're going to define something called HF red. So basically, the idea is there's a class in the knot flow homology that sort of corresponds to like HF hat of S3, quotient by that class. And once you've thrown that out, that's what we're calling HF red. And as long as that HFK hat red has different maximal non-trivial Maslov gradings, well, that's what we mean by sufficiently different knot flow homology. And then the exotic R4s that you get are going to be distinct. Great. Okay. So if you have slice knots with sufficiently different knot flow homology, then you get distinct exotic R4s. A natural question at this point would be, well, like how hard is it to cook up knots with sufficiently different knot flow homology? It's not hard, so we just give one particular infinite family. So if you take the I would think of these as generalized square knots. So take T2n, connect summit with minus T2n, where n is at least 3 and odd. Well, then you're going to get out distinct exotic R4s. Questions at this point? Oh, do different slice disks for the same? So that's something that our techniques aren't going to see. So I don't know the answer to that. More exercise for Zhangtao?
Yes, I'm your pigeon.
So maybe it's the same question, but I was just wondering what happens if you choose different Casson handles?
Oh, I'll say a little bit about that later, but the quick answer is we can't really say much about different Casson handles. Okay, terrific. Okay, now I'm going to tell you a little bit more about Casson handles. Great, so first let me remind you about an ordinary 2 handle, so D2 cross D2. This is how we draw it, as we all learned in our favorite textbook, Gompf and Stipschutz. Okay, well now imagine that your 2 handle had a self-intersection. Well, it's an exercise in the aforementioned Gomp-Stipschitz that, in fact, here is a handle diagram for sort of this immersed disk with a single self-intersection. Remember, these self-intersections have a sign. And so here I've drawn the Whitehead link, and the sign of the self-intersection informs the sign of the clasp in that Whitehead link. Okay. And now, okay, well, if we had a disk right here, then we could get rid of the self-intersection. But then sort of things would become boring. So we don't want that. But what if we have the next best thing, which is if we have another disk with a self-intersection sort of attached along here, and then the corresponding handle diagram would look like this. And now, okay, well, we have this problem that we're trying to get rid of, the self-intersection. And now, well, what if we just, keep on going? And then sort of the miracle that happens is that sort of you can keep on doing this and sort of push the problem off to infinity. And this is how you build a Casson handle. And so the Casson handles in our theorem are the simplest possible Casson handles with all positive clasps. So I'll call those CH+. What kind of variance could you have? Well, you could have different signs of these self-intersections, and those would give you different signs on these clasps. What other variations could you have? Well, a disk could have multiple self-intersections, and then you would get sort of multiple of these one handles here, and then they would sort of branch, and you can get more complicated Casson handles that way. But the ones that we work with are the simplest possible, all positive Casson handles, drawn here, CH+. Okay, and so, well, for our exotic R4s, we can give an explicit handle diagram for them, right? Because, well, okay, take your favorite ribbon knot. I guess today my favorite ribbon knot is this pretzel knot. From Gomp and Stipschitz, we all learned how to draw handle diagrams for ribbon disk complements. Here is a ribbon disk complement for this pretzel knot. And then if you want to attach the Casson handle to this ribbon disk complement, well, there's your picture. And now, well, if you wanted to use different ribbon knots in this construction, well, just replace that ribbon disk complement with whatever your favorite ribbon disk complement happens to be. Okay, so I want to tell you a little bit about what was previously known about this question. So in 1992, D. McCullough and Friedman showed that if you have a fixed ribbon disk complement and you vary the Casson handle, you can get uncountably many exotic R4s. Since the uncountable part is showing up, well, their argument, they used a cardinality argument, and in fact, the explicit Casson handles are unknown for this uncountable family. What else is known? Pichotsa Gomp, so they showed that if you use this -3 pretzel knot and CH+, well, versus if you use sort of the negative of that knot, the 3 -3 3 pretzel knot, and the all negative Casson handle, CH-, those are distinct exotic R4s. Okay, so I want to spend the rest of today telling you about how we proved this result, and our proof relies on something called N-floor homology, which was defined by Gadgil about 15 years ago. Okay, so our goal is to study a non-compact Floer manifold. So I think most other results using Heegaard Floer homology focus on compact manifolds. So how do we use the Heegaard Floer package to study non-compact manifolds? Well, maybe the first question is, so how are you going to think about our non-compact manifold? So let's think about an open Floer manifold with one end. And so we're going to describe that open Floer manifold with an exhaustion. So basically, we're going to have a family of nested compact Floer manifolds, X0, X1, X2, et cetera. sort of nested inside of each other, and then sort of the limit of this thing is going to be the airflow manifold. And then, well, we cut it up into these pieces, and then it's also helpful, so here, the boundary of x naught is y naught, boundary x1 is y1, and then if you sort of look at x1 minus x naught, well, then you're going to get this four-manifold, which we'll call W01, and it's going to be a cobordism from y naught to y1. So you can see already how this is sort of going to start fit into the Heegaard Floer package. You know, we have a four-manifold cobordism between two closed three-manifolds. Those are things that we know how to deal with. So this is going to be how we describe our open four-manifold. OK, to get things to work nicely, we need to put a few mild hypotheses on the algebraic topology of the things involved. So the first one is sort of to deal with some spin C technicalities. So you need this map on homology to be surjective, the map from H1 of Wij to H1 of Yj. And then the other one is we need sort of some gradings on our tools, and to get the gradings to work out, we need B2 of x1 and B3, B2 of xi and B3 of xi to be 0 for all I. Okay. And so now that we've described our four-manifold this way, well, now we're going to use the Heegaard Floer package. So maybe I'll pause here for questions to give Zhengtao some more exercise.
Yeah, maybe one question. What we want is to use the Heegaard Floer homology between the three manifolds that are cobordant to each other with W.
Say that again.
Maybe, I mean, Y0, Y1, and Y2 are three manifolds.
That's right.
Yeah, so we want to look for Heegaard Floer homology of these three manifolds?
Yes, that is going to be one of the key ingredients in our proof.
OK, thanks.
How do you get uncountably many options into this construction?
How do you get uncountably many options? So I'll be honest. So we don't get any uncountably many options, but sort of for these, when you vary these Casson handles. So for example, even for sort of if each of your disks only has a single double point, well, you can vary the signs. So like the sign of the double point can be positive or minus, and so then you have the sequence that can be, you know, a sequence where each element is either plus or minus.
Oh, OK.
Yeah.
Thank you.
And then you can get even more than that by sort of branching and having more double points in each immersed disk.
And just a quick, naive question about terminology. What is an end?
Oh, an end is just like when it goes off, going off. Going off to forever. So for example, I only have the dots and going off in one direction, but if they went off in both directions, then I would have two ends.
Is there a formal definition to this, or?
There's a formal definition.
OK.
Yeah. No more exercise for Zhengtao? Great. We'll give him an opportunity later for more exercise. OK. So Heegaard Floer homology, one of my favorite tools in low-dimensional topology. Great. So Peter gave a great introduction this morning. So to a closed-oriented three-manifold Y, you can associate its Heegaard Floer homology. The Heegaard Floer homology comes in lots of different flavors. There's something called the plus flavor, where you invert U and then you quotient by F adjoin U. And then it turns out, then you get sort of this, you have this infinite tower, which you can quotient by. Great. You have this infinite tower that you can quotient by, and then this is other summand, HFred. HFred is great. It's great because it's a finitely generated graded vector space. So if you're not an expert in Heegaard Floer homology, we'll just think about to a closed-oriented three-manifold, we're getting a finitely generated graded vector space, HFred. And that's the version that we're really going to be working with today. And one of the terrific things about Heegaard Floer homology is that you have these cobordism maps. So if you have a cobordism W between yi and yj, well, then you're going to get a map that sort of descends to HF red. So you're going to get this map from HF red of the incoming side to HF red of the outgoing side. And sort of we're eventually going to be applying this to sort of this exhaustion for our four manifold. Great. OK, so we have these cobordism maps. Terrific. We're very happy. Heegaard Floer homology is TQFT-like, so if you stack together two cobordisms, well, you would expect the cobordism map to be the same as just for the sort of bigger cobordism. That is true. There's maybe some spin-C hypotheses that I'm burying under the rug, but you should just think about it that you stack cobordisms, and then the composition of the maps is the same as for the big cobordism. OK. And so now in this setup, what do we have for ourselves? We have a directed system. So what is a directed system? Well, for us, it's going to be a collection of graded vector spaces, HF red of these yi's. And then you have these maps, FWIJ, that basically takes you from HF red of yi to HF red of yj for any pair ij where j is bigger than y. Great. So we've built a directed system. What can one do with a directed system? Well, one can take the limit of a directed system. And that's exactly what Gadgil did when he defined N-Floer homology. Great. OK. So N-Floer homology is the limit of this directed system. I can remind you what a limit of a directed system is. So take the disjoint union of all of these HF reds. OK, that's going to be quite large. And then we're going to quotient by an equivalence relation. And so what is the equivalence relation? Basically, two things get equated if there's some map that sends them to the same thing. That's what this is saying. So xi is equivalent to xj if there exists some k bigger than I and j, such that fwik of xi is fwjk of xj. So that's what N-Floer homology is. Great. OK. And so now you might ask, well, what's the N-Floer homology of some of your favorite open four manifolds? Maybe your favorite open four manifold is R4. And then, well, it's a nice exercise. So I'll tell you the fact that HF red of S3 is 0. And then from that fact, well, you should think of a particular exhaustion for R4 and use that exhaustion to compute that the N-Floer homology of R4 standard is 0. OK. So now our goal is to use N-Floer homology to show that we can get this infinite family of explicit exotic R4s built from ribbon disk complements and Casson handles. OK. So if we want to use Gomp's example, well, here's the ribbon disk complement for that pretzel knot. Here's a positive Casson handle. Great. OK, so now I need to give you an exhaustion for this four manifold. So my x naught is going to be the ribbon disk complement. And then we're also going to be interested in the boundary of this. So the boundary of this, well, the boundary of the ribbon disk complement of k is just going to be 0 surgery on k. And now, well, what's our next piece going to be? Our next piece is going to be, well, attach this 1 handle and attach this 2 handle. That's going to be our x1. And now, well, we also need to know what the boundary y1 of x1 is. That's a great exercise in Kirby calculus. Does anyone in the audience want to volunteer what the boundary of x1 is? Terrific. Yeah. It's going to be 0 surgery on the Whitehead double of k. Great. You get an A. All right. And in fact, OK, so now that I've sort of done x1, well, maybe you can guess what the rest of them are going to be. And now maybe I'll ask the question, OK, well, what's the boundary of x2 going to be? This question's probably easier now that you know the first answer. Everyone's too shy. OK, great. Yeah. So it's going to be the whitehead double of the whitehead double of k. And so as you keep going, well, you're going to get iterated whitehead doubles. You're going to get zero surgery and iterated whitehead doubles as you sort of keep on going out. Terrific. OK, great. So we're doing this n for homology. So we're taking this direct limit. OK. OK, we want to show that so our first goal is to show that these give us exotic R4s. So since R4 standard has trivial n-floor homology, well, to show that these are exotic, it'd be sufficient to show that their n-floor homology is non-trivial. So the easiest way to do that would be, well, if all of these cobordism maps, if they were all injective, that would mean that nothing ever died. And because these three manifolds have non-trivial HF-red, if all of these cobordism maps were injective, nothing would ever die in this direct limit, and so then we could show that the n-floor homology is non-trivial, and we'd be happy. That's what we really wanted to happen. Like the next best thing happened, which is like they weren't quite, like this is sort of a theme in Heegaard Floer homology. It's like, oh, you have some dream that's going to make your life like really easy, and then you're like, your dream isn't true, but if you use gradings, then your dream is going to be true. And then depending on the particular situation, like how much worse using gradings makes your life really varies. Fortunately, in this situation, using gradings didn't make our life that much worse. But basically, you use the gradings, and then sort of things are injective in the right gradings, and then you can show that the n-floor homology is non-vanishing for these things. Great. So now we've boiled our goal down. Well, we want to show that sort of these cobordism maps are, almost injective in certain gradings. OK. Great. So in order to do that, well, we need to compute these cobordism maps. So the cobordism map, so sort of like, generically, if we're sort of like n steps out at xn, we're going to be looking at the cobordism map from zero surgery on the n-fold iterated whitehead double of k to zero surgery on the n plus first iterated whitehead double of k. And that cobordism map is going to come from attaching this one handle and then attaching this two handle. OK. Well, right, so Peter had limited time, so he didn't talk much about cobordism maps this morning. But the cobordism maps, well, they're described in terms of handle attachments. So I guess we attach the one handle first. Great. So we're here attaching this one handle. All right. Well, what's going to be the three manifold that we get after we attach this one handle? Well, we just connect some on with S1 cross S2. And then Heegaard Floer homology satisfies a Kunith formula. And then, so it turns out that when you connect some with S1 cross S2, you basically just get two copies of the Heegaard Floer homology of the other summand. There's some grading shifts. That's what you get. And then the cobordism map for attaching a one handle is very simple. It's just that basically you have your Heegaard Floer homology of y, and then it just gets sent to sort of this copy of the two copies of the Heegaard Floer homology of y that appeared in the connect sum. So the upshot is one handles are not complicated. We completely understand it. That's not where we had to do any work. OK, so where did we have to do work? OK, well, now we're attaching this two handle. Great. And so this work was done before I heard Adam's talk today. So do you notice this, this two handle? It's attached along a curve that is not null homologous. And in general, if you're not an expert in sort of the bordered surgery modules, well, then computing cobordism maps for attaching something along a non-null homologous knot is difficult. And so first we were like, OK, how do we do this? This looks hard. How to compute this? But now if you remember from Peter's talk this morning, What's one of the best things about Heegaard Floer homology? Well, one of the best things about Heegaard Floer homology is that it satisfies the surgery exact triangle. Okay, so our goal is to compute the cobordism map for attaching this two-handle. And so, well, okay, so the first picture, well, the two-handle isn't there, so that's like doing the infinity filling along this knot. Well, we want to understand the cobordism map for this zero-frame two-handle. And so, well, if you have the infinity filling and the zero filling, well, Peter described this exact triangle where you need to have the curves to sort of, he drew that hexagon. The curves need to all intersect once with the appropriate sign. And so can someone tell me what the other filling along this curve should be so that these fit into an exact triangle? Patricia is great. Lots of people are doing the thing that my undergrad class does when I ask them a question, is they hold it up in front of them. Yeah, so terrific. The answer is 1. Okay, so the point is that these three manifolds fit into a surgery exact triangle where we're doing the infinity filling, the zero filling, and the 1 filling along this curve. Okay. So we want to know the Heegaard Floer homologies of all the 3 manifolds in this picture. Okay, so let's start. Bless you. Let's start with the picture in the top left. Great. Okay. So this 3 manifold. Well, the 3 manifold. Great. Oh yeah. So I'll call these manifolds y infinity, y0, and y1. So up here we have the manifold y infinity. Well, the 3 manifold is just zero surgery on the n-fold Whitehead double of k, connects some S1 cross S2. Okay. Great. So we want to compute the Heegaard Floer homology of zero surgery on this n-fold Whitehead double. As Adam described, well, if you know the knot Floer homology of your knot, then you can run this mapping cone formula to compute the Heegaard Floer homology of surgery on your knot. So we want to know the knot Floer homology of this Whitehead double. Well, fortunately for us, Matt Hedden computed the knot Floer homology of Whitehead doubles. So that's our first ingredient. Then we're going to use the Ozsvath-Szabo surgery mapping cone to compute the Heegaard Floer homology of zero surgery on this knot, whose knot Floer homology we knew. And then connect summing with S1 cross S2. That's just the Kunith formula. So we know the Heegaard Floer homology of this corner of our exact triangle. And similarly, well, for the other corner, this is just zero surgery on the n plus first Whitehead double of k. So using the same ingredients, Matt Hedden's computation of the knot Floer homology of Whitehead doubles together with the mapping cone gives us that. Okay, and so now we come to this mysterious bottom piece that is surgery on some 3-component link. There's this mapping cone formula for surgery on a knot. There's also a link surgery formula developed by Manolescu and Ozsvath for surgery on a link. That is a great formula, but I've never actually used it in practice. I guess in their paper they use it to compute surgeries on the Hopf link, which are just lens spaces, and that's the most complicated example they do in their paper. And so that's not something that we wanted to use to compute this. So we tried to think of, well, how else could we compute the Heegaard Floer homology of this manifold here? Great. So we've reduced our problem now to understanding the Heegaard Floer homology of this 3-manifold. Okay. Great. So here's the surgery exact triangle. We're trying to compute this third term here. Okay. Well, we've all read Gomf and Stipschutz. So, well, does anyone look at this and is there something they might want to try to do to simplify this diagram? Great. You could slide. That's one thing you could do. What else might you want to do? Is that a twist? Great. Great. We're developing our own sign language for great. So we want to great. we want to do this twist. Was that? Great. Okay. So you want to blow down that +1, and then you get this 2-component link. Okay. So we've gone it from a 3-component link to a 2-component link. That's pretty good. Okay. And so now, now we have this 2-component link. And now let's think about this 2-component link. Let's think about it as a purple knot in the 3-manifold at 0 surgery on this other component. So we have this. So now basically the dream is, well, if we can compute the knot flow homology of this purple knot, and I'm very happy at this point because this purple knot is null homologous in this 3-manifold, and then I do know how to run the mapping cone formula on a null homologous knot. So the dream now is to compute the knot flow homology of this purple knot sitting inside the 3-manifold given by surgery on the black component. Okay. And I also look at this and I say, well, this is a connect sum of 2 things, right? It's a connect sum of this Whitehead double and this knot J sitting in Y. And why is this helpful? Well, there's a Kunith formula for knot flow homology. So to take the connect sum, you just take the tensor product. And, well, this summand, right? So this is just a knot in S3. And we know how to compute the knot flow homology of Whitehead doubles in S3, thanks to Matt Hedden. And so now, really, all we have to do is compute the knot flow homology of this knot J in Y. So now we've broken up our problem down further, and now our goal is just to understand the knot flow homology of J in Y. Great. OK. And so like many knot flow computations, you don't want to do this from the definition. You don't want to draw a doubly pointed Heegaard diagram and count holomorphic disks. At least I don't want to. So again, you want to use some tricks. And so let's think about what we know about our knot J. So what do we know about our knot J? If you do -1 surgery on J, that basically will undoes this -1 full twist on this component. And so then if you do -1 surgery on J in Y, well, the 3-manifold that you have is just 0 surgery on the unknot, so it's just S1 cross S2. So that's some information about our knot J. We know what 3-manifold we get if we do -1 surgery on J. What else do we know about J? Well, J has genus 1. You can sort of take this disk and then take sort of a hollow handle that goes around here. J has genus 1. And let's also think about what do we know about the 3-manifold Y that our knot is sitting in. Well, Y is 0 surgery on the trefoil. You can check that the black knot is just the right-handed trefoil. And so it's straightforward to compute 0 surgery on the 0 surgery on the right-handed trefoil. It has basically the simplest possible Heegaard Floer homology that it could have, given its homology, and then it has some gradings. Okay. So this is all information that we know about Y and this knot J sitting in Y. And so the main idea is that our knot Y has no HF red. So in a sense, L spaces are typically rational homology spheres, but sort of the definition of an L space is that it's a 3-manifold whose HF red is trivial. And so sort of morally, maybe I'll think about L spaces as 3-manifolds that have trivial HF red. And so in that sense, this manifold, Y, has trivial HF red. Moreover, -1 surgery on this knot J also yields a 3-manifold that has trivial HF red. So sort of the moral idea is that, well, we have a 3-manifold that's a lot like an L space. We have a knot inside of that 3-manifold that behaves a lot like an L space knot. -1 surgery on it is giving us basically an L space. And then if you've studied L space knots in S3, you know that their knot flow homology is sort of very constrained. And so the point is that this knot J in Y behaves a lot like a genus 1 L space knot. I guess technically it's a negative L space knot. But if you have a genus 1 L-space knot, you know it's not Floer homology, and that same argument applies in this scenario with sort of the extra complications that you're not in a rational homology sphere. You have to use the gradings a little bit too, but that's the general argument. Okay, and so the great news is that that information is sufficient for us to determine the knot Floer complex for this knot J in Y. And then the knot we were actually interested was the connect sum with this Whitehead double, so you use the Kunith formula. And so we needed to know the Heegaard Floer homology of Y1 sitting on our surgery exact triangle, and then that was what we did using this argument. Great. So we're interested in the exact triangle for these 3 manifolds. And what does the answer look like? This is what the answer looks like. So great. So this, for the experts in the audience, this T plus is sort of this infinite tower part. And then we get some HF red. I haven't, for simplicity, I've not written any of the gradings. I haven't said too much about this sort of T plus business because basically in the exact triangle, the T pluses just like all cancel with one another. So for all intents and purposes, you can just ignore them in terms of the exact triangle. And so then what you're left with is these 3 pieces. So you have something of rank 2n, something of rank 4n, and something of rank 4n. Okay, and then it's a nice linear algebra exercise to show that these are what the ranks of those maps have to be. And then remember, the hope was for this top map to be injective so that when we took the direct limit in our directed system, we got something non-trivial. Well, now we see, well, it's not injective. It doesn't have rank 2. I mean, it doesn't have rank 2n. It has rank n. But again, if you use the gradings, you can see that, well, the gradings of the pieces for which this is non-vanishing, that's good enough for us to get what we want. The ranks are not enough, but the gradings save the day. Great. Okay, and then the upshot is, well, this shows us that the n Floer homology for these manifolds is non-trivial. So this shows that if you start with a non-trivial slice knot and you attach this all positive Casson handle, you get an exotic R4. Well, our main theorem also said that if you had knots with different knot Floer homology, in the appropriate sense, then you would get different exotic R4s. And basically, if you trace through gradings in this whole recipe, basically the maximal graded piece of HFK red of your starting knot, that governs the gradings on the n Floer homology. And basically, that determines the maximal graded piece in the n Floer homology where you see something non-vanishing. So maybe the sort of upshot of that is that the gradings on the knot Floer homology determine the grading where you see non-trivial n Floer homology. Determine the gradings where you see non-trivial n Floer homology. And that's how you can distinguish this countably infinite family of exotic R4s. Okay, and so as promised, well, I want to say a little bit about other Casson handles. That would be really great. So the first other Casson handle that we looked at was all negative signs. Okay, so you can run the same argument doing this computation. So basically, the clasp is going to be different, and then you run the same argument. And then you get the exact triangle. And then basically, the relevant portion of the exact triangle looks like this. Remember, the map we were really interested in was this top map. And now, okay, so I guess it's a linear algebra exercise for the audience. If these are the ranks and this is an exact triangle, what's the rank of this? Yeah, great. I agree with the very sad face that, yeah, so sort of, you know, no matter what gradings or other things you show at this, there's just no hope here. And so this is in fact, right, and so this here is, so if you have sort of Right, so we looked at sort of taking all positive whitehead doubles. So basically, if you put in a single negative whitehead double somewhere, well then, when you stick that in, you're going to get 0, and you won't be able to use Floer homology to say anything. So it's very sad. But maybe to be slightly more optimistic, you can say things. We can say things about other Casson handles, right? So I mentioned you can have these branching Casson handles. So you can describe your Casson handle like with a tree. Basically, this is saying, oh, your first disk had 2 self-intersections, one second disk had 1 positive and 1 negative, and as long as you have 1 infinite positive chain, that's enough to sort of take our argument and stick it in and say that the Floer homology is going to be non-trivial. So that's something somewhat more optimistic. Great. And then maybe the other thing I want to say is there's this question about, well, using other slice disks. And so Floer homology, it's like, right, so it's this direct limit. And basically, like, with a direct limit, you can you don't have to start at the beginning when you take a direct limit. You could start further out, and the answer is going to be the same. And so when you see that you can start further out, you can see that, well, then it's not going to depend. It's not going to see which slice disk you started on, because you could start further out and it would just be 0 surge around whatever iterated whitehead double and doesn't see what came before. So this method isn't going to be useful for say, using different slice disks for the same knot and seeing if those give you different exotic R4s. Great. And so thanks for your attention.
Okay, so thanks for the wonderful talk, and any questions from the...
I kind of want to go a little bit further back in your talk. I guess I'm still a little bit confused about this exhaustion and how, I guess I was trying to think about things that aren't just cylindrical ends that you could build exhaustions for. So I guess, could you explain more about how one could come up with it? How do you choose these yi? And then also, why is this Floer homology independent of those choices?
Great. So so for the first question, was it about how we came up with this exhaustion for a particular?
Not for this particular one, but just in general, there must be some sort of okay, you pick or way to pick all these hypersurfaces, and then you look at in between. How does that work if it's not just obviously a cylindrical end?
Yeah, I think. I think it's not obvious. Sort of. So we're in the situation where sort of there's a natural exhaustion.
Okay.
Yeah, but so your second question, the second question was about, well, right, so in this definition of Floer homology, I said pick an exhaustion, take this limit. So you need to show that the limit is independent of the choice of exhaustion. Great, so when you have, if you're taking a direct limit, you can always pass to subsequences, and then the limit is going to stay the same. So if you have 2 different exhaustions, well, okay, you can always pass to subsequences of those 2 exhaustions so that the pieces, the 2 exhaustions get interwoven. So you're if you have an exhaustion for call it X and an exhaustion X prime, well then you pass it so it's going Y1, Y1 prime, Y2, Y2 prime. So the 2 exhaustions alternate. And then sort of for formal properties of limits, that's enough to show that the limit's going to be the same.
Okay, that makes sense. Thank you.
What if you take an inverse limit? Instead of taking the direct limit with CH minus, you take the inverse limit. It looks like you're flipping the maps around. You look at the opposite exact triangle, you get not injectivity, but something close to that. And,
yeah, that's a great question. We haven't thought about that. Excellent. Zhengtao is getting exercise as I promised him.
The three manifolds wide, and in this situation, they're not homology spheres, they're homology S1 times S2s. Is that inevitable from the topology of R4s, or an essential part of this method of calculation, or it just happens to be?
I think it just sort of happens to be, yeah.
If you don't work with HF red and just work with HF hat, do you also get is that well defined, and do you get a preferred element in the end for homology?
Oh, if you just work with HF hat, that's a great question. I think you probably, it's in like Gadgel's definition of n-flow homology, it's important to sort of not have you don't want like the T plus sort of sticking around, because like that'll just sort of like always live around. So if you work with HF hat, I'm just guessing, you might need a way to sort of identify like which part is like coming from the tower. So maybe it's minus will work with plus would be my guess.
So the question is, so the motivation was because if you get a preferred element, then the question would have been whether that could distinguish, like if you started with different slice disks, then
I guess, the question was starting with different slice disks. I think sort of if you're using this direct limit, the direct limit isn't going to see anything about starting with different slice disks. So I think you would need like a different approach to answer that question.
Even if you started with a preferred element in the homology group?
Oh, even if you started with a preferred element, I'm not sure about that.
Why did you start with a ribbon disk instead of a slice disk? Does it make a difference?
No reason. You could start with a slice disk. I mean, I guess if you want to draw like a curvy diagram for the complement, I'm much better at drawing curvy diagrams for ribbon disk complements. Maybe there are people in the audience who don't have that skill issue.
Okay, so if there are
there's one more.
Thank you. It's a short question. Have you used this n-Floer homology to study like non-compact cobordisms of three manifolds or non-compact four manifolds apart from R4?
I have not, no.
Oh, okay. Nice. Thank you.
Any other questions? So if no, let's thank Jen again. So this finished today's talk, and we will meet again tomorrow at 9 a.m., the same room. And also, if you participate in any activities in this afternoon, you may sign up in any of those WhatsApp group outside, and please also check the meeting time outside, okay? All right, so thank you. Have a good day.